engagement. Good evening, everyone. I am delighted to be here and grateful for the
be addressed in the last 5 minutes of the session. So kindly note them down as the session progresses. This session is being recorded for further reference. So let's gear up for an engaging session.
Alexander Sean, Head of Development and Robotics Engineering at FKS Maschinenbau GmbH, Berlin, on advancement in human-robot collaboration and AI-driven automation. The event culminated in a MOU with signing with FKS Maschinenbau GmbH, which will open doors for internships and global career opportunities for our students. In November 2024, our college's computer department had organized a successful faculty development program on research opportunities in sustainable development using GIS. In June 2024, we successfully conducted the International Conference on Recent Trends in Science, Technology and Management, a hybrid event reflecting our commitment to academic excellence. Our institute has been honored with several prestigious awards, including the Best Women's College Award of 2019. In India, the Best College Award among 17 institutions nationwide by the FSAI and College of Substance Award from the Natarajan Education Society. Additionally, we have received the third Best Engineering College Student Chapter Award from the Indian IEI, the Best Engineering College Student Chapter Award 4 times from the IET Center Pune, and the Best Changemaker Award for our NSS activities from Savitribai Phule Pune University. I am also proud to share that our college magazine has been recognized as the best magazine for 5 consecutive academic years by Savitribai Phule Pune University. We are also thrilled to announce the establishment of a dedicated computer center equipped with 150 state-of-the-art computers to enhance learning for both students and faculty. As part of continuous growth, we have submitted proposals for several key projects, including an AICT funded Idea Lab proposal in association with Excel 3D, seeking funding rupees 97,17,146 for the academic year 2024 and 25. Aim at the fostering innovation and interdisciplinary learning. Wi-Fi facilities have been established across the campus and hostel, ensuring seamless consecutive for all academic and research purposes. In terms of placement, we have proudly reports that 137 students were placed in multinational companies last year, with 32 students securing offers with salaries of over 8 lakh per annum, and one of our outstanding students, Utkarsha Kakade, was placed with Walmart Global Tech at an impressive 22 lakh per annum. Total 2,088 students placed to date. Over the years, our faculty members have filed 30 patents, published over 900 research papers, and contributed significantly to academic and research communities. We also have an active NSS unit with 250 volunteers and a strong alumni network supporting our student career and entrepreneurial aspirations. We are proud to announce that Ms. Vedika Rajamani, third year Electronics and Telecommunication Engineering students, represent the Institute at the prestigious Republic Day Parade in New Delhi. Today's faculty development program is an opportunity for all of us to learn, collaborate, and enhance our knowledge. Let us take full advantage of these sessions and discussion to not only refine our technical expertise, but also reignite our passion for teaching and inspiring the next generation of global leaders. I look forward to the fruitful exchanges and collaborations that will emerge from this program. Thank you and wish you all a productive and inspiring evening ahead. Thank you, everyone. Thank you so much.
Thank you, sir. Now I would like to invite Dr. Surjit Singh, sir, to enlighten the audience.
Good evening. Thank you, madam. Good evening to all of you. Uh, Today, chief guest, Dr. D.V. Jadhav ji, principal professor and Dr. Pradeep V. Yadav, Madam Anjali Kadam, and Dr. Aswini Ranade, and other faculty members and professors from the college. So,
Sir,
yeah, am I
Surjit
audible?
Singh, sir,
Yeah.
please switch on your camera.
Okay. It is on camera. Am I visible?
No, sir.
It is showing that camera is on.
Okay, sir. So no issue.
Oh, now visible, madam?
Not yet, sir.
Okay.
Please
But
check
it
from
is
your
showing.
side. Please check from your side.
Yeah. From my side, it is a camera is on.
Okay.
Yeah. Should
Okay,
I continue?
sir. Okay, continue,
Okay.
sir.
So, as already introduced, that the National Institute of Hydrology is also conducting lot of training courses for various officials from various central government organizations and state government. We also train various field engineers, research scholars, and students. And For the first time, I am seeing that we are also jointly conducting this training course for the faculty of an engineering college. So I am very delighted and I congratulate to the organizers for conducting this training course. And Let me first introduce about our institute. So, our institute, the National Institute of Hydrology, has mandate to undertake, promote, and coordinate systematic and scientific studies in all aspects of the hydrology. And Next mandate is to cooperate and collaborate with other national and international organizations in the field of hydrology to establish and maintain a research and reference library in the field of hydrology, and to do all other such things as the society. NIH is governed by a society under the Ministry of Jal Shakti. So, whatever society advise from time to time for various hydrological problems study related to hydrology that are conducted by NIH. And the National Institute of Hydrology, it is an autonomous institute. It is under the Union Ministry of Jal Shakti. It is a central government office, and NIH has its headquarters at Roorkee, and we have 6 regional centers, and those centers are located one in Jammu, one recently opened in Jodhpur, one is Bhopal, and another is at Belgaum, Patna, Kakinada, and Guwahati. So, for solving the regional problems across the country, the centers have been created. And NIH is a ISO 9002 certified institute. And here at headquarters, we have 6 divisions working in different domain. Like there is one surface water hydrology division that caters the study related to surface water related. Then another division is groundwater hydrology division to cater the problems related to groundwater. Then another division is environmental hydrology division, and there is water sources system division, hydrological investigation division, and myself is heading here is Center for Cryosphere and Climate Change Studies. So this Center for Cryosphere and Climate Change Studies Center, it was recently created 2 years back because a lot of glacial lake outburst events are happening nowadays, and also the climate change is impacting various sectors. Looking the need, the center was created, and here at NIH we are also having different laboratories. So like we are having a soil and water laboratory for testing of soil samples for determining the hydrological soil properties. Then we have a well-established and very renowned nuclear hydrology lab where we are testing various isotopes in water and finding the source of recharge uh, and leakages from them. So isotopic technique, nuclear hydrology lab is established. Then we also have here a cryosphere and GIS lab for remote sensing and GIS related activities, and also the glacier related activities. Then we also have a very good water quality laboratory. So for testing the water quality in surface water, groundwater. So we are having a very good equipment here, and also speciation of various metals like arsenic. So we have number of equipment and very good laboratory. And also we have a groundwater modeling unit for groundwater related study. Then there are various other activities conducted by NIH. We are doing basic and applied research, user-defined demand-driven research project. Number of public sector organizations, government, state government, they are approaching to NIH for conducting hydrological studies. Uh, then we are also conducting R&D projects. We are also doing the sponsored project from DST, UNDP, World Bank, UNESCO, and also private agency, also like Hindustan Zinc Limited and public sector NTPC. So various organizations they approach us wherever there is some problem related to either environmental problem or groundwater related issues problem or flood related or area drainage mapping kind of problem. So they approach to NIH, and we also provide consultancy services by conducting very good research. And besides this, we are also doing the capacity building, under which we are doing organizing international and national conferences and training programs. Almost we can say that every week NIH is also conducting a training program, both in physical mode as well as in online mode and hybrid mode. Besides NIH at headquarters, our real center, they are also conducting number of trainings. Then we also have a mandate for software development related to the hydrological studies. And we also contribute, NIH also contribute in policy planning at a national and international level. And for public awareness, we are also conducting mass awareness programs. We go to the nearby areas for school children, for various communities. We are educating the common public for issues related to water, how to conserve water, how to protect water, how to protect water from pollution, and also promotion of scientific studies in Hindi. Every 2 years, we are also conducting a national conference in Hindi where all the publications are submitted in Hindi language and also presented in Hindi language also. And in the next month, in the month of March, we are also conducting a international conference on groundwater that is scheduled from March 3rd to March 6th. So NIH has very strong R&D capabilities covering flood and drought studies, water source system analysis, hydrological modeling, water quality assessment and modeling, groundwater modeling, regional hydrology, climate change impact studies, integrated water resources management. And about the center, the Center for Cryosphere and Climate Change Studies. So it has a vision to provide leadership in cryosphere and climate change studies through cutting edge research to facilitate water resources management. Uh, not taking much time, I stop myself here, and I congratulate to the organizations, to the organizers, and all the faculty members. The course content the organizers have formulated, that is very relevant in current time, and it will definitely enhance the knowledge and make aware the various issues related to climate change and water sector, and will definitely help to the faculty members. Thank you very much.
Thank you so much, sir.
Thank you, sir, for sharing the valuable information with us. Now, we have a chief guest, Honorable Dr. D.V. Zadav, sir. He couldn't join today because of the convocation program, but he has conveyed his best wishes for the FDP. So, we will continue with our next schedule. Moving ahead, we have another esteemed guest joining us for the today's program, Dr. Ashwini Ranade, ma'am, Scientist D Center for Cryosphere and the Climate Change Studies, National Institute of Hydrology, Roorkee, India. Now, I would like to request Dr. Ashwini Ranade, ma'am, to briefly introduce the FDP course. Over to you, ma'am.
Thank you so much, madam. And very good afternoon to all of you. And I'm not the guest here because I am also part of this course. So my responsibility is also equally like Sonali, madam. So respected chief guest of the today's function, Dr. D.V. Zadav, Dr. Surjit Singh, sir, Principal, sir, Dr. Pradeep Zadav, and Coordinator, Madam Dr. Sonali Kadam, and my all dear participants. So on the behalf of National Institute of Hydrology, I again welcome you all for this 6-day ATAL online faculty development program, which is jointly organized by Bharati Vidyapeeth College of Engineering for Women and National Institute of Hydrology, Roorkee. And today I am very much delighted to share some of the details of this course. So as we all know, and Madam also has already explained that AICT's ATAL FDP, which is an initiative to enhance the skill and knowledge of the faculty members of all the different academic institutions and make them aware about the different new emerging techniques and advanced fields, and try to feed the gap between the researchers and the academicians as well as industries. So in this ATAL FTP program, AICT has suggested 8 different themes and subject areas in order to organize the FTP course. So in this course, we have selected the topic of the navigating the climate variability and impacts of effective water management, disaster preparedness, resilience, and mitigation. So this topic itself is a very vast, very emerging, and as Dr. Sujit sir already said, that it is a dire need of the country. So to cope up for the climate change issues, especially the effects on the water, weather, maybe health, economy, agriculture, energy, in all different aspects. So we need that it is required an interdisciplinary approach to get prepared to adapt and to mitigate for this climate change issues. And we really need the people from different diversified background areas that may include scientists or technologists, architectures, or social scientists, maybe economics, industrialists. So different type of peoples are really required to come together and to address this climate change issue. So by keeping in this mind, we have developed this course and to make aware all the participants about the recent developments in the climate change issue. So specifically, we have divided this course into 4 subgroups. Like in the first, it is hydrology and water resources, which is like in hydrology, water availability, water quality issues, flood monitoring issues, or studies related to the glacier, it will come. Then second is weather and climate science, so which especially includes the monsoon, extreme rain events, climate change impact assessments, numerical weather prediction, climate modeling, then climate change mitigation, adaptation, atmospheric aerosols, air pollution, all these things comes under this subgroup. Then the third part is the environment and ecology, where we will going to explain the land use land cover changes, how they are affecting the climate change, and then ecological resilience, then greenhouse gas emissions, carbon footprints, and then disaster management, that is different technologies for the flood and disaster management. So in on all that, the whole course is divided into the 4 parts, and this course we will going to conduct into the 30 sessions, and each day we are planning for the 2 sessions that will be conducted at the evening time. And all the resource persons which are going to give this lecture, they are very experienced scientists and professors from different research organizations, from different academies, colleges, and even from the industries. And out of these 13 sessions, especially I would like to highlight that 2 sessions are we will going to exclusively conducted by the scientists from the foreign universities. So that will definitely help you to know more about the climate change issues, not only in India, but on the international scale. So few things which I just want to convey you before the start of the course, that at the end of the course, we are going to conduct the online test, and that will be means after successful completion of the course, that is we need 70% marks of that course, and you also should have 80% attendance in each of the session, and then only we will consider it as a successful completion of the course, and then the certification will be granted. So more details Dr. Sonali madam will also share with you in that case. So also I just want to convey that these sessions are going to conduct on the Microsoft Team platform, and all the sessions, the attendees, they should log in from their registered email account, because the attendance will be automatically recorded from the Microsoft Team software. So please remember that you please log in from your registered account. And also I hope that you will find this course very much helpful and interesting for your future endeavors and in your respective case in whatever field you are working now. So we try to design the course in such a way that each and every participant from this course will get benefited in some or other way. So I strongly request you and suggest you to kindly actively participate in this course and session and make this course successful. So on this note, I wish you best of luck for this course, and I hand over this session to Dr. Sonali. Thank you so much.
I sincerely appreciate you, ma'am, for sharing your incredible knowledge and enlightening the participants. Now, I would like to request Professor Anjali Kadam, ma'am, to deliver the vote of thanks.
Thank you, Jayashree. Good evening, everyone. As we come to the end of this wonderful inauguration ceremony, I would like to take this opportunity to extend my deepest gratitude to all those who have made this event a resounding success. Firstly, I would like to express my heartfelt thanks to our distinguished speakers who have so generously shared their invaluable insights and expertise with us. Your words have set the tone for what I am sure will be an enriching and inspiring faculty development program. We are truly grateful for your time and contribution. A special thanks to ATAL Academy and the National Institute of Hydrology for their continuous support in organizing this event. I especially thanks to our principal, Dr. Pradeep Zadhav sir, our faculty members, and all those involved in the smooth conduction of this event. Your hard work behind the scenes has made this event seamless and engaging, and we are deeply appreciative of your efforts. Finally, to all participants, thank you for being part of this FDP. Your enthusiasm and dedication are what make this program truly meaningful. As we now begin the first session of the program, I request everyone to remain in the same meeting. I am sure you are all eager to dive into the discussion and sessions ahead. Thank you once again. Let's make this an unforgettable and impactful experience. I request all dignitaries and faculty participants to switch on cameras for group photo to make this moment memorable. हाँ. हाँ. ग्रुप I request now, without further ado, I would like to hand over the mic to Professor Varke ma'am, who will take us through the first session of the exciting journey.
Experience. Now it's my privilege to introduce our esteemed speaker for this session, Dr. Ashwini Ranade, Scientist D, Center for Cryosphere and Climate Change Studies, National Institute of Hydrology, Roorkee. Dr. Ranade ma'am holds a post-graduation in physics and an MTech in atmospheric sciences from the University of Pune. She completed her PhD in atmospheric and space sciences from the prestigious Indian Institute of Tropical Meteorology, Pune. She has been awarded several prestigious fellowships during her career, including the Indian Institute of Tropical Meteorology Scholarship and the DST Young Scientist Fellowship. Dr. Ranade has served in several renowned organizations, including Ministry of Earth Sciences, New Delhi, the National Center for Medium Range Weather Forecasting in Noida, and the Birla Institute of Technology, Misra. Currently, she is a scientist D at the National Institute of Hydrology, Roorkee, under the Ministry of Jal Shakti. Her primary research interests include global climatic change, the Asia-Pacific monsoon, and extreme hydrometeorological events. Dr. Ranade has made significant contributions to academia, guiding numerous postgraduate and doctoral students. She has published over 32 research papers in national and international journals, along with book chapters, research reports, and popular scientific articles. In addition, she has presented her work in over 50 national and international scientific conferences and symposiums. Dr. Ranade served as a reviewer for many national and international journals specializing in hydrometeorology and climate change. She has also organized several national and international training courses in hydrometeorology and climate change. Dr. Ranade has successfully led and completed numerous research projects sponsored by Ministry of Earth Sciences, the Department of Science and Technology, and the National Institute of Hydrology. So we are honored to have you, Dr. Ranade ma'am, and look forward to your valuable insights. Over to you.
Thank you so much, ma'am. Am I audible now?
Yes, ma'am, you're
Okay, ma'am.
audible.
Yeah, yeah. Let me share my screen then. Is it visible?
Ma'am, it's visible.
Yeah, it's a full screen, right?
Yes, yes.
Okay, okay. Thank you so much, ma'am, for the introduction. And now we will begin with our first lecture of today's session, that is on the nexus of climate change and monsoon dynamics and extreme events. So, as we all know that there are millions of people are all across the world or even South Asia, they are depends upon the monsoonal rains and for their livelihood. But the same rain, which if it happens unprecedentedly and at wrong time, then they can disturb them as well. So that is because of the climate change. So this climate change is not only altering the monsoon, but it is amplifying the signal of the extreme rain events also. And that is earlier we have not seen like that. So it is very important to understand the nexus between the climate change, monsoon, and extreme rain events. So, and that will be not useful just for the scientists or researchers, but for the policymakers, for the planners, and for other communities, social communities also. So, let us move ahead and explore it in more detailed way. So you can see that on day-to-day basis, we have seen these newspaper articles based upon the changes in the weather and climate and monsoon. So they are only not in the newspaper, but we can see it on the TV channels also, or even social media. So completely, we keep on flooding these things mostly during the monsoon season. So they just have to the how the climate change is evolved nowadays in recent years and becoming the greatest environmental threat because of this. And we can say that there is a no place on this earth remain now which is free from any kind of disasters, maybe cyclones, maybe cloudburst or floods, droughts, earthquakes, heat waves, or any every part of the earth is in a threat of this type of disasters. So let us start from the climate change. First, I will going to give an overview of the Earth's climate system, its variability, forcings, and then we will see the climate change. What does mean by climate change and its complexity? Why it is so much difficult to predict the climate? And then monsoon. What is the monsoon system? And then onset and withdrawal of the monsoon. What is the definition of the onset and withdrawal, how the India Meteorological Department defines the monsoon, declares it, and then some intra-annual or intra-seasonal variability of this monsoon. Means I'm not going to in details, but I just have to give a flair of all these topics which are there in the research from the research perspective. Then El Nino and monsoon relationship, we always keep on talking, and so monsoon relationship, and then extreme rain event characteristics, and then some case studies also. I will explain that how meteorological analysis can be done on the extremes, and then how weather monitoring and forecasting takes place nowadays. And lastly, we will summarize the how climatic changes overall affected the market. climate change. Rises.
Ma'am, your voice is
Yes.
breaking.
Yeah. Voice is breaking.
Yes, ma'am. It's not audible.
Not audible.
It's not audible.
Just a minute, madam.
Ma'am, you're not audible. Ma'am, you have to unmute yourself.
I will share it again. Okay. Now it is
Hello.
okay.
Anjali madam, please call her.
Hello.
Yes, ma'am. Now it's audible.
Hello, madam. Is it okay? Hello.
Yes, ma'am. Yes,
Am I
yes,
audible?
ma'am. Yes, you are audible.
Hello.
Yes, ma'am. You are
You
audible.
are audible, madam. Please continue.
Hello. Audible now?
मॅडम त्यांनी म्यूट केले बघा.
Hello. Am I audible now?
Hello. Unmute.
Hello. Hello. Yeah. Am I audible?
Sure.
Yeah. Sorry for the disturbance. So we have seen that these current weather and climate change scenarios, that concentration of the carbon dioxide is also currently very high, 425 parts per million. And then Antarctic sea ice extent, if you see, that is a record low. This is 1.5 million square kilometer below average. And
similarly, there are many more signals we are getting, like retreat of the glaciers, especially declining trend in the snowfall, snow cover area, or glaciers are there seen in the recent decades. So if you see in the recent Hindu Kush Himalaya, then there is 10 to 15 meter per annum retreating trend is seen in the glaciers. And then ultimately there is a change in the extreme rain event characteristics, as we know that there is a rising trend in the frequency and magnitude of the extreme rain events. And we have seen that there are the areas where floods are occurred which were earlier not considered flood prone. And every year you can see that more than 7.5 million hectares of land is affected, and 1,600 lives are lost. So these types of signals are really alarming to us, and thinking about to study more and to understand more about the climate change. So let us start with some basic things, that what is Earth's climate. So you can see that Earth's climate is, you can divide into the 5 spheres. You can say like atmosphere, hydrosphere, lithosphere, cryosphere, and biosphere. So you know that atmosphere, that means weather, then radiation, clouds, different greenhouse effect gases, all these things comes under the atmosphere. And then hydrosphere, which is related to the water, global water cycle, then oceanic water, ocean currents, and then tides, tsunamis, and all other carbon dioxide sinking of the into the ocean. So all these studies are related into the hydrosphere. Then there is a lithosphere is also there, where we can all consider related to the rocks and soils and volcanic eruptions. Then the cryosphere is there, where all different forms of ice, snow, and glaciers, permafrost, and different things are going to study in the cryosphere area. Then there is a biosphere, where especially the related to the vegetation, soil, and different types of organisms, and how there is exchange takes place between the biosphere and different spheres are there. So in addition to that, there is one more sphere is now added into the Earth's climate system, that people say it is like a anthroposphere. So which is especially related to the human induced processes, or gases, deforestation, desertification, and different greenhouse gas emissions. So that additional sphere now we have to taken into consideration. So now let us see that how the climate is changing, and what are the things which are forcing the climate to change. So we know that there is a change in the climate from one year to another, and in year to year changes in the climate or weather, that is uh, caused by the different phenomena. But those things which are there from the changing from the thousands to millions of years, they are having the different causes. So in that, plate tectonics is the one of the major variability thing, that where we can have that the surface of the earth which is made up of the different plates, and then the plates are keep on colliding with each other, and because of that earthquakes and volcanic eruptions are also formed. But this movement of the plates are very slowly. So because of this plate tectonics also, climate of some part of the area can be changing. Then there are orbital changes are there on the earth's parameters, like shape of the earth's orbit. Then there is a tilting of the earth's axis, or wobbling of the earth. So all these parts, they are especially affecting the climate from thousands, means 100 to 100,000 to 10,000 years on that scale. Then another one is the solar variability. As we know that sun's radiation is one of the important parameter for the Earth's climate system. So whenever there is a drastic change in the solar parameters, then they can also affect the climate. Then some oceanic parameters are also there. Then we know that aerosols, greenhouse gases, and all these things, they are also affecting the climate. And then on a smaller scale, we can have the atmospheric circulations are there. Then land use, land cover changes, sea ice extent, these are also affecting the climate on a smaller scale. So you can see that if you want to know the Earth's radiation balance, then we can understand the in more details how the temperature is warming nowadays. So if Earth's radiation balance is generally measured at the two places, one is at the top of the atmosphere and another one is at the surface. So at the top of the atmosphere, how much is incoming from the space, that has to be balanced by the amount which is reflected back, and amount which is outgoing or emitting. and at the surface how much is absorbed by the Earth's surface and how much is emitted. So this Earth's radiation balance determines the Earth's temperature. So you can see that on an average, if you see near the in the tropics, there is a positive balance is there. Means incoming is more than that of the outgoing. But in the extratropic and polar areas, this balance is negative. Means radiation is deficit. But if it will continue, then is it like that tropics are keep on warming and warming forever and the poles are cooling forever? But it is not like that, because there is a transport of energy takes place from the one part of the globe to the other part of the globe. That is called transport of the energy and momentum. So that is also one of the important parameter in the Earth's radiation budget. Now comes to the greenhouse effect. Nowadays we are always keep on blaming the greenhouse effect is a bad thing, but natural greenhouse effect is very much important to us. That I will just show you the thing. Hello, am I audible now? Yeah.
Yes, ma'am, you
So,
are perfectly audible.
yes, okay. So you can see that in the natural greenhouse effect, you can have sun's radiation comes on the earth and one third part of it is reflected or re-radiated back, and that determines the temperature of the earth. But if some part radiation will not get absorbed, then earth's temperature would have been in the negative side. But because of the greenhouse gases, natural greenhouse gases, that is water vapor is one of the important greenhouse gas, and then carbon dioxide, then Earth's temperature try to maintain in a position where people can stay comfortably. But nowadays what happens, that human enhanced greenhouse effect is there. That is because of the anthropogenic activities like GHG emissions or vehicular emissions, and different emissions are there which comes from the industries or power generation. And because of that, whatever the amount which is coming onto the surface of the earth, that is re-radiated back, but that is again absorbed by this type of air pollutants, and because of that earth's temperature is rising. So here you can see in the one of the simple example, that if we want to calculate the Earth's temperature, then there is a simple formula that how much amount of radiation is lost and how much is comes on the Earth. If you balance it, then you can get the temperature of the Earth. So here you can have the how much energy is lost, that is your circumference, then transmittivity, and from the Stephen's law, if you equate with the incoming solar radiation, that is solar constant, and this is the alpha is the albedo. So that albedo will take care of the how much amount of energy will be reflected back to the surface. Then if you solve this, then you can see that temperature of the earth could be minus 18 degrees centigrade if you balance the earth. But right now temperature is not 18 degrees centigrade, it is 15 degrees centigrade. So that is 15 degrees centigrade, that is means 33 degrees, they are the natural greenhouse effect of the earth's atmosphere. So because of the natural greenhouse effect, we can have the temperature of the earth is in the positive side. But nowadays this is not only 15 degrees centigrade, but it has been risen because this greenhouse effect warming is enhanced. So there are also some feedback mechanisms which are also contributed into the climate, that is called positive feedback and negative feedback. So when you see the positive feedback, that means some signal is there, it initial some change happens in the atmosphere, then it amplifies keep on the because of the feedback. And in negative feedback, what happens, it reduces whatever initial change is there, that has been reduces and try to stabilize the system. So there are four major feedbacks are generally studied, that is ice albedo. One is ice albedo feedback, that if warming is there, then there is a melting of the ice and glaciers, and then there is a decrease in the albedo, that is reflected radiation. So if the radiation gets decreased, reflected, then more and more radiation will get absorbed, and because of that warming takes place and more ice melts. So this keep on happening, that is positive feedback. Then there is a ocean and carbon dioxide feedback. So as you know that ocean is one of the major absorber of the carbon dioxide, but it can absorb the carbon dioxide only in case that if the temperature of the ocean is cooler. If ocean gets warmer, then what happens? It will release the carbon dioxide, and more carbon dioxide is again added into the atmosphere. Because of that, then again greenhouse gas warming takes place, and this greenhouse warming again warms the ocean, and again ocean will release the CO2. So this absorption of CO2 gets decelerated, so that this type of feedback is again contributing into the warming of the planet. Then there is a water vapor feedback that is similar to this, that if there is a change, climate temperature change is there, then there is a change in the atmospheric water vapor also takes place, and then there is a change in the greenhouse effect. Then one of the very interesting feedback, that is a cloud feedback. So in cloud feedback, what happens? That depends upon the position of the cloud, where the clouds are there. So if you see the high clouds, then what happens? High clouds, they transmit the radiation more, and whatever they emitted by the earth, then they reflect it again back. So they are ultimately heating the atmosphere. But if you consider the low clouds, then what happens? Whatever the amount is there, that will reflected from the top of the cloud, and the amount which is emitted from the surface, that is also emitted through the cloud. So in short, low clouds are they are cooling the atmosphere, in short. So now comes to the climate change. How to define the climate change? So there is one always thing is that what is the difference between climate and weather? So we are using this terminology synonymously many times, but weather and climate are different things. So of course there is a not a sharp boundary as such is there, but there is a change. So when you talk about the current state of the atmosphere, then you call it as a weather. But if you talk about a mean state of the atmosphere for a longer period of time, then we consider it as a climate. Now, what is the climate change? Climate change. So if we want to define the climate change, then we can define it as there should be significant change in the climatic conditions. So climatic conditions over the earth, like radiation, temperature, pressure, wind, cloud, precipitation, and many more. So during a specific period compared to the preceding period, capable of causing the considerable impact on the settled ecosystem. So here settled ecosystem is one of the important term.
Ma'am, you are not audible again. Participant, wait for some time. Ma'am is rejoining. There is some technical issue at her end.
Hello, am I audible now?
Yes, ma'am. Perfectly audible.
हेलो।
Yes, ma'am.
हाँ, एक्चुअली यहाँ बार बार डिस्कनेक्ट हो रहा है कि ट्राइंग आउट ऑफ द मीटिंग करके मैसेज आता है मुझे बार बार, पता नहीं क्यों।
Okay, I will check.
इज इट
You
ओके
please
नाउ?
continue. Yes, yes. You are now audible.
Okay. So we are discussing about the climate change. As I said, there is no specific definition does exist which is globally accepted for the climate change. But we are sure that climate change is gradual rather than abrupt, and climate change is relative rather than absolute. So now let us try to understand the complexity in the climate change issue. So if you see the complexity, then I think my slides are not moving, right?
Ma'am, it's moving.
Hello?
Right now it is showing complexity in temporal resolution of climate change.
Yeah, that is okay. Yes, yes. So if you see the complexity of the temporal resolutions, then you take any climatic parameter, say temperature, and if you plot the time series for a longer period, like hundred thousands of year, then you can see that there are few millennia which can be seen as a warmer, and there are few millennia which can be cooler. So in each millennia, if you go down, there are few centuries warmer, few centuries cooler. And in again in one century, there are few seasons warmer and few seasons cooler. And in a season also, you can have the intra-seasonal variability that few days are warmer and few days are cooler, like that. So the time scale is very important in the in the defining the climate change. And also this time scale for the study varies from the scientific disciplines. If you study the time climate change in the geology, biology, or ecology or oceanography, then they are million to billions of years people are studying the climate change. Then anthropology or archaeology, people used to study few tens of thousands of years. Then history, philosophy, spirituality, religion, literature, then 100 to few thousands of year changes are considered in the climate change study. Then we are studying the climatology, meteorology, or hydrology. Then there are few days to few centuries are there. And you can say that if you see media and press, then few hours or few days change also media reported as a climate change. So there are different time scales that exist according to the different disciplines. Now come to the Holocene climate change. So if you see the northern hemispheric temperature change from the last 10,000 years, then you can see that there is a end of the last glacier period happens about 11,000 years back, and after that northern hemispheric surface temperature, which is fluctuating from the 15 degree plus minus 0.5 degree or 1 degree centigrade. Okay. So here you can see that 15 degree centigrade temperature is very crucial for the monsoon or rainfall occurrences over the, especially over the Indian condition. So it has been seen that if the temperature goes below the 15 degree centigrade, like here you can see the blue epochs, then that time there was a drier condition, especially over the Indo-Gangetic plains. But when the temperature fluctuates between 15 to 15.5 degree centigrade, something like today's thing, then there is a Indo-Gangetic plain or most part of the country is getting the rainfall. But when the temperature goes beyond the 15.5 degree centigrade, sometimes it happened in the history, then that time it has been seen that monsoon has been shifted westward, and there is a drier condition over the Gangetic plain, but western part of the country like northwest India, Rajasthan, they are getting the good rains. And right now we also see the similar type of thing. So when we try to compare this with the culture of the country, then we can see that changes in this climate is closely connected with the culture of the country. So I am not going into details in that, but only just want to highlight that whenever there is a, good monsoon was there, then that time what happens, the Indian mass or psyche of the Indian people was towards the materialism, power, or health, or something like that, or commerce, trade. They are more concentrated on that. But whenever there was a drier period was there, when temperature was less than 15 degrees centigrade, so that time monsoon was not good. So that time what happens, people move more towards the spirituality, philosophy, religion, literature. So that time most of the social transformer those are there, they born during this period of drier period. So it has been seen that there is a culture of the country is closely related to the climatic changes. So now coming to the monsoon, as we all know that monsoon is affecting the economy of the country in different ways. There are different sectors are there, from the water resources or industries, transport, energy, tourism, everywhere monsoon is affecting the country. Now, if you see that not only India is getting rain monsoon, so there are four major monsoon systems are there, which are there all across the globe. That is Asia Pacific monsoon, which covers the South Indian monsoon. We also call it as a South Asian monsoon, then East Asian monsoon, Southeast Asian monsoon, and then Western North Pacific monsoon. Then there is a African monsoon is also there, where it is West African and East African monsoon is there. There is a American monsoon is also there, Northwest American, South American monsoon is there, and then there is a Australian monsoon. So different monsoon systems are there. But in that Asia Pacific monsoon is the one which is the major means thing which is we can see it actually. So other monsoons are not that much prominent as like a Asia Pacific monsoon, and Indian monsoon is a part of that Asia Pacific monsoon only. Now let us see some of the history of the monsoon. We can see that it is one of the oldest weather phenomena which is happening over the earth, and which can delineate the difference in the weather from cool dry winter to hot wet summer. So this monsoon area generally defines the area which is between the two routes called silk route and spice route. So earlier days, this silk route and spice route, Arab traders are used for their trading. They carry the silk from the China, Mongolia region, and they trade it into the Arabian countries, Persia, Egypt, Arabia. And also through this spice route, they carry the spices from this equatorial islands as well as India, and then also they trade to the this Middle East countries. So for these traders, they need the wind direction so that their travel could be easier. So this that time they use the word mausim, because this mausim or mausam that comes from the Arab traders. That is mausim. That means the thing which comes once in a year only. And as we say that monsoon comes once in a year, so it is this monsoon term comes from this mausim. So historically, monsoon is the realization of the reversal of the sun and rains, not winds. But nowadays we call it as the reversal of the wind for the monsoon, because that is the phenomena or thinking which is comes from the navigators, not from us. So if we want to define the monsoon in short, then we can say that monsoon is a massive thermally direct circulation system which produces summer seasonal rainfall across Asia Indo-Pacific region, which is bounded by the continental silk route and oceanic spice route. So how this tropical circulation system matters or works, that also we will going to see now. So there are people in history, they try to understand the monsoon and put different mechanisms or hypotheses to define the monsoon. So first hypothesis is given as a differential heating. So in 1686, Halley defined the primary cause of the monsoon as the temperature contrast between the land and ocean. So it could cause pressure difference, and then because of the pressure difference, wind moves from the high pressure area to low pressure area, and that we call as a winds. Then later different many scientists are there also there. They say that no, that is a gangetic land sea breeze, because that time we don't have that much data set is available. So whatever is you can see from your eyes, that only be considered and defined. Then second hypothesis has been given as the migration of the ITCZ. So this ITCZ is still there, that is intertropical convergence zone. That is the convergence between the two types of winds, equatorial trough and means tropical easterlies from the southern hemisphere and from the northern hemisphere, and they combine over the equatorial region. That convergence zone is called the ITCZ. So it has been seen that during January, this ITCZ blue color, it is located in the southern part of the globe. But in July, this ITCZ shifted towards the Indian continent. So you can see that this movement of the ITCZ or migration of the ITCZ is maximum over this Indian Ocean region. That's why whatever the region comes between these, they are experiencing the monsoon season. So now let us try to see the what drives the monsoon. So this motion of the or migration of the ITCZ, that is because of this Tibetan plateau. So this Tibetan plateau plays a very important role in the migration of the ITCZ. Why? Because this Tibetan plateau, if you see, it is having the extent of 2000 to 2500 kilometer, while vertically it starts from the 4000 kilometer up into the air. So at that height, this Tibetan plateau is heated. So middle of the atmosphere is heated at that height, and which has the capability to bring the winds from the oceanic region to the Indian region. So in addition to that Tibetan plateau, there are different temperature contrasts are also there, which are also contributed to the monsoon. That is temperature contrast between two hemispheres, between tropics and extratropics, between land and sea, between lower and upper atmosphere, and then between Tibet and different parts of the heights. So these temperature contrasts are also important for the monsoon. Then there is a Coriolis force, which is the Coriolis force is a fictitious force which is happening because of the rotation of the earth, that we feel that winds are tilting towards the right in the northern hemisphere and towards the left in the southern hemisphere. So this Coriolis force also contribute into that. And then there is another important parameter, which is interaction of the winds, that is mid latitude westerly winds and wet moist easterly winds, which are there coming from the Indian Ocean. So they are also interacted, and different moist processes are also there, which determines the intensity of the monsoon. So in order to understand this circulation in more detail, first we have to understand how the general circulation of the atmosphere takes place. So you can see here is as a earth as a globe, and this red arrows indicate the lower wind motion, and this blue indicates the upper air wind motions. So this is at the surface, and this is, you can say, at the top of the atmosphere, or you can say 10 to 12 kilometer above into the air. So if you see, you can divide this earth into different zones. So we know that there is a equatorial low pressure zone, subtropical high pressure zone, then subpolar low pressure zone, like that. These zones are there in the southern hemisphere also. And there are winds, tropical easterlies, they flow from the subtropical to equatorial belt. Then westerlies are there from subtropical to subpolar belts. So by considering all, you can see that there is a rising motion over the tropical regions, and there is a sinking motion over the subtropical regions. Similarly, there is a rising motion in the subpolar region and sinking motion in the polar region, and again in the subtropical region. So whenever there is a sinking motion is there, then any weather system is, there is no possibility of formation of the weather system. So you can see that subtropical regions are those regions where mostly all the deserts of the globe are present. So if you divide and try to understand the global precipitation pattern as a whole, then you can see that in the equator, there is a precipitation is there throughout the season. Means there is no as such monsoon or 4-month season takes place in the equatorial belt. Throughout the season, precipitation is there. Then if you see in the tropical belt where our country locates, where we are getting the precipitation during the summer, but winter is dry. Of course, in some part of the country like extreme North India and Himalaya, winter rainfall is also there. And then subtropical region, as I say, there is a very less precipitation or no precipitation at all throughout the season. That's why it is a desert area. Then in the subtropical, extratropical region, you can say that winter is wet and summer is dry. So these areas are getting precipitation during winter, but summer is dry. Then in subpolar region, there is again ample precipitation is present throughout the season. And then polar regions, there is a very less precipitation exists throughout the season. So like that, you can divide whole the globe into the different precipitation belts. Now try to understand the monsoon and try to visualize the monsoon circulation. We just consider monsoon as a rainfall, but how it is happening, what are the winds actually takes place, and how the whole circulation of the globe changes during the 4 months of the season. So this is the schematic we have prepared to in order to understand the monsoon. For any layman can understand this thing. So here this round thing you can see, these are the pressure belts. So in all across the globe, there are different pressure belts are exist. Low pressure and high pressure belts are there. So there are 8 different high pressure zones are there, which are already present throughout the year over the globe, and they are the oceanic highs. We call it as a oceanic highs. So they are the center of action for this monsoon circulation, like North Pacific high, Azores high, North Polar high, then South Indian Ocean high, Australian high. So different highs are there. Then there is one Tibetan high is there. That is not the permanent. That is a semi-permanent system. You can see the country India is over here. So this Tibetan high forms only during the monsoon season. And one major peculiarity about this Tibetan high is that this high is there is a low pressure at lower level and high pressure at upper level. But in all other parts, these highs are high pressure throughout the vertical column of the atmosphere. And another peculiarity is that if when these all highs are from the surface to 500 hectopascal, that is means about 5 to 6 kilometer up into the atmosphere, but this Tibetan high is from the surface to 10 to 12 kilometer. So you can see that how intense this high is there. So this low pressure at the lower level and high pressure at the upper level, which is created the convergence of the wind at the lower level and divergence of this wind at the upper level. So these blue arrows, you can see these blue arrows are at the surface winds, and these red arrows are at the upper atmosphere winds. So you can see that from all across the globe through different highs, this winds converges into this low pressure area over Tibetan region, then there rises, and this big amount of mass that has been diverted to the different parts of the globe or different high pressure cells, and this completes the monsoon circulation. So when you say the monsoon circulation, that means the air comes from the lower level from different heights concentrated over the Indian sub-region, Asian continental low or Tibetan low at lower level, rises and diverted to the different parts of the high. So if this Tibetan anticyclone is very intense, that indicates that your monsoon is very much intense. And this location of the Tibetan anticyclone also determines the spatial extent of the monsoon or rainfall in different parts of the country. So if that is westward or that is westward, or if that is shifted into 2 or 3 cells, that determines the different spatial nature of the monsoonal rains across the country. So we will see more details when we see the extreme rain event case studies. So now consider, see here the actual picture of the wind. So these are the streamlines. So streamlines means the winds which we plot on the weather chart to understand from where they are coming and where they are going. So you can see this is the July-August picture. So this is the surface layer, means at the lower level. So you can see that these winds from the different southern ocean, they are crossing the equator and coming over the Indian subcontinent, taking meander and merges over this Tibetan high or Asian continental low over here. And in upper part, you can see that that is about 12 kilometer or 13 kilometer high. You can see this circulation picture that is called Tibetan high. Just now we have seen. So this Tibetan high, what happens? This air is circulated over here and it diverted to different parts of the globe like that. So this completes the picture of the monsoon. So this monsoon circulation you can see only during the monsoon season. In other parts of the
Ma'am, you are on mute. Sorry, you are not audible.
Ma'am, unmute yourself. Ma'am, unmute yourself. Both the speakers, like mics are muted. Please unmute.
Ma'am, you are on mute.
Yeah, ma'am is joining from another device. Please wait.
All participants, it's a humble request to please mute your mic, except the speaker.
Ashwini ma'am is in now.
Available now?
Ashwini ma'am, your voice is breaking.
Now I'm audible. Joined from my mobile now.
Yeah, you are audible now.
Okay.
Please share your present. Yeah, it's shared only. Share it again.
I don't know why I'm coming out of the meeting every time. I have logged in from the two accounts.
Yes, I can see that, but ma'am, share it your presentation now, and you're audible now.
It is already there.
Yes,
I can see.
yes, ma'am. Your presentation is shared.
So here you can see the monsoon, how it is spreading the country from the 1st May to 31st September. So this is for the 2020. So this monsoonal area, blue region is showing the monsoonal area. So if you want, I can run it again. This is spreading from the Kerala and extreme northeast India to the extreme northwest and Rajasthan, and again receding back. So generally we consider it as a it can clearly seen that this is the monsoon is nothing but the spreading and intensification of the equatorial atmospheric conditions over the that part. So now coming to the onset and withdrawal of the monsoon. So this onset and withdrawal of the monsoon is one of the important things which everybody wants to know, that how they are determined and what will be the onset in each year, something like that. So we know that Indian Meteorological Department, they periodically updated this criteria of the monsoon and onset and withdrawal of the monsoon. So first time IMD has given the criteria for in 1943, that is for the normal onset and withdrawal dates of the monsoon, and that is based upon the 180 rain gauge stations. So that time this onset and withdrawal has been given for the British India. So present day, that is India, Pakistan, Bangladesh, Myanmar, Sri Lanka, and that time only the criteria was the characteristics monsoon rise or fall in a pentad rainfall. Pentad means 5-day rainfall total. If there is a sharp rise in the 5-day rainfall total, then the monsoon is declared. Then after that, many times criteria have been revised. So in 1967, Ananta Krishnan has given the criteria that from the 10th May, if at least 5 stations out of 7 stations in the Kerala, if they report the 24-hour rainfall 1 millimeter or more for 2 consecutive days, then the second day of that month has been advanced over the Kerala. So this criteria was available with the IMD, and IMD used that criteria till 2005. But then it has been realized that it is not correct to only define the onset and withdrawal based upon the rainfall. Because many times it has been seen that we are getting the bogus monsoon onset. So then other atmospheric parameters are also started to incorporate it. Then in 2006, IMD has adopted the Pi and Rajivan criteria, and they have again modified it 2007 and 9 as well. So in that, what they have defined that after 10th May, if 60% of the 14 selected stations, if they report the rainfall of 2.5 millimeter or more for 2 consecutive days, then the onset of the monsoon over the Kerala may be declared on the second day. And along with that, depth of the westerly winds over the Arabian Sea and outgoing long wave radiation, which is an indicator of the convection, that has also been taken into consideration. But then in 2016, again IMD has given in very detail the criteria that how the onset and withdrawal dates has to be defined. So currently this criteria IMD is using. So that depends upon the first the rainfall. That rainfall should be 2.5 millimeter for 2 consecutive days over 10 to 14 selected stations in Kerala after 10th May. Then there is a specific rise in the zonal wind that is more than 15 to 20 knots. And that depth has to be up to the 600 HPA. That means that wind should be up to the 4 kilometer up into the atmosphere. And then outgoing long wave radiation should be less than 200 watts per meter over the Arabian Sea region. And then there should be maximum cloud zone. All these things has to be there. Then onset of the monsoon we can declare over the Kerala region. But still IMD is not having the criteria that how onset and withdrawal can be defined in other parts of the country. So further advance is declared based upon the advancement of the rainfall and maintaining the spatial continuity of the rainfall pattern and the northern limit of the monsoon. Similarly, withdrawal criteria is also there, which withdrawal is attempted after the 1st September. There should be cessation in the rainfall activity. There should be anti-cyclonic circulation over the region, and different other criteria are there. So these are the criteria where IMD is currently used for the declaration of the onset and withdrawal of the monsoon over different parts of the country. Now, recently, IMD has also given some normal dates. So earlier in 1943, as we say that IMD has given the climatological or normal onset and withdrawal dates. But now it has been seen that because of the climatic changes, these dates are no longer applicable. So IMD has modified the climate changes. Now, based upon the what it has been modified, I am not going into that detail. That is a little bit complicated. So I will just want to show you that how the earlier onset date, normal onset dates, and how new onset dates are looks. So here you can see that this dotted red line are earlier onset dates, and this green lines are current onset date. These are the normal dates. These are not year-to-year dates, normal dates. Like normally we say that on 1st June rainfall occurs or onset of monsoon happens over the Kerala region, like that. So here in new dates also onset of the monsoon over the Kerala is again 1st June only. But there is a change now that earlier up to 15 July, monsoon completely covers the entire Indian subcontinent. But now it has been said that it is covering much earlier, that is up to 8 July only. And in the withdrawal phase, there is from the 1st September to 15 September is the withdrawal phase of the monsoon for whole country. But now it has started from the 17th September. So here withdrawal is little bit delayed. So you can see the clear-cut signal of the climatic changes that monsoon is arriving early and going late. So the whole monsoon duration is now extending. So these are the new onset and withdrawal dates of the monsoon. So if you see the special distribution of the monsoon, then you can see that how each day to day, how rainfall changes from one part of the country to another part. So it is, you can see that from 1 to 2 millimeter per day to more than 40 millimeter per day rainfall happens all across the country. And mostly the higher rainfall regions are coastal regions or hilly regions are there. So if you see the seasonal rainfall pattern, then there you can have different groups of the rainfalls. Like If you consider, suppose Northeast India, then Northeast India is getting extremely high rainfall, while Indo-Gangetic plains are getting less rainfall. Like Northeast India, more than 2,000 to 8,000, 10,000 millimeter rainfall is their seasonal rainfall. But in Indo-Gangetic plain, you can have about 800 to maybe 1,200, 1,300 millimeter rainfall. Then if you come to the peninsular India, then peninsular India is still less, from 600 to 1,400 or 1,300 millimeter. And if you go to the Rajasthan region, then you can see that this rainfall is very less, means less than about 300 millimeter rainfall happens in the country. So there is, you can see that there is a large spatial variability of the monsoon rainfall exists across the Indian subcontinent. Now coming to the interannual monsoon rainfall variability, you can see that interannually, this is the longest instrumental rainfall series from 1813 to 2020. So this series has been divided into the different quintiles and different parts, from very dry to very wet, based upon the amount. So you can see that there are different epochs can seen in monsoon rainfall throughout the region from more than 200 years of record. So here you can see that mostly this is the dry epoch, then again wet epoch is there, then there is a fluctuating epoch, again some dry epoch is there, and now there is a wet epoch, dry epoch. So like that, year to year basis, all India monsoon rainfall changes. So if you see the month-to-month variability, then June, July, August, September, you can see that month-to-month you will not able to see any significant long-term trend. So, but there are some recent epochs are there where you can see the significant declining in the rainfall. Like August rainfall, you can see that in recent 10, 20 years there is a decrease. You can see then in July rainfall or even June rainfall is there. But if you see more than 200 years of record, you can see that all India monsoon rainfall series is homogeneous and random, not much changes seen. So if let us see the statistics that annually India is getting 1165 millimeter rainfall, and monsoon rainfall is about 900 millimeter, and there is a standard deviation of 100 millimeter in annual rainfall and 88 millimeter in monsoon rainfall. Then CV is also there, highest and lowest rainfall also is there. So that statistics is based upon the 1813 to 2015 data set. Now, if we want to see the drought and flood year and how the spatial structure of the monsoon changes, then you can see the departure from the long-term mean. That this is the JJAS rainfall in centimeter during the drought year 1987 and flood year in 1988. So you can see the drastic change is seen in the immediate years from 87 to 88, how the rainfall structure pattern has been changing. So interannual variability is also sometimes very sharp is happening. So no need to say that this year monsoon is good, so it is not necessary that next year monsoon will also be good. Then if we see that trend analysis, then you can see that 15 year, 31 year, 51 year, if you want to see, then as I say, that climate change is relative phenomena. So if you consider the recent 15-year changes with respect to all 200 years change, then you can see that there is a 2.8% decrease is seen. Now, if we change your window to 31 year, then there is a 1.1% decrease. If you again increase the window to 51 year, then recently you can see 6% decrease. And if you consider whole 101 year window, then you can say that there is no decrease, but there is an increase in the monsoon in recent 101 years as compared to the past 200, more than 200 years of record. So depends, that trend, it depends upon the, with respect to what previous data you are comparing. Now for the hydrology and water resources purpose, we just want to know what are the recent changes are there. So in recent 15-year changes, you can see that how the rainfall, monsoon rainfall is changing. So here you can see major part of the country, there is a declining trend is seen in major part of the river basins across the country. And in Northeast India, peninsular India, there is a increase in the rainfall. So this gives the complete picture of the river basin rainfall in the recent 15 years period. Now coming to the intra-seasonal variability. So as we see that even though monsoon season is from the June to September, but not necessary that rainfall will happen throughout the season. because rainfall always happens in the form of the spells. So they happen for few days, and again there is a dry spell, again there is a wet spell. It is happening like that. So here you see that this is extreme southeast peninsula, like the Tamil Nadu or Kerala region, where there are a lot of spells are happening. So this green indicates the wet spells and orange indicates the dry spell. So you can see that lot of spells, more than 11 spells are happening in this part of the country. But if you see the Rajasthan region, then very less spells are happening. Sometimes there are years there are no spell at all also. So this intra-seasonal rainfall variability is also varies a lot all across the country. So if you want to see complete picture of the spells, so here you can see that there are spells varies from the 3 to 4 cells over the extreme North India to 11 spells over the extreme southern peninsula. And if we consider the country as a whole, then we can say that for the country as a whole, there are 6 wet spells happens and 5 dry spells happens, and the rainfall also changes. Then duration, if total duration, if you see, that is of 55 days only, and intensities of 16.7 millimeter per day is happening during the wet spell. And the start of the spell happens out 31st May, like start of the monsoon from the 1st June. So it matches with that. And end of the spell happens in the 8th October. So during the monsoon season, this contribution of the spells, that is 68%. And dry spell is of the 17%. Now, if you see in more details, then there are very interesting characteristics we can see in the intra-seasonal variability of the monsoon. So as I say, that country, normally we are getting the six wet spells and its duration is 9 days. But the dry spells, they are of 14 days duration. And number of spells varies from 11 to 4. So this dry spell duration is longer than that of the wet spell duration. So this sequence of the spells, that shorter wet spells and longer dry spells, they are showing that evapotranspirational demand is higher. So this is more conducive for the agricultural and ecological activities rather than hydrological and water resources. Because for hydrology and water resources, what we want wet spells of longer day duration so that we store the water in our reservoirs. And if moderate rainfall intensity wet spells are happening for a longer period, then that means they are recharging the soil. So they are more conducive for the agricultural purposes. So in that respect, we are lucky that our spatio-temporal variability or intraseasonal variability of the rainfall is conducive for the agricultural, but they are not favorable for the hydrological or water resources purposes. So you can see that green water flow, so that is actually potential evapotranspiration and green water storage, which is stored in the soil moisture, and less blue water flow, that means water which is stored in the reservoir and water which is going into the deep aquifer recharge. So this partitioning is not equal. There are inequalities there. So this we need to taken into consideration while we are planning for the agricultural or for the hydrological perspective. Now, in the climate change perspective, we have seen that in recent years, wet spells are slightly shorter duration and rainfall intensity is higher, but dry spells are longer duration and rainfall intensity is weaker. So these are the 19 sub-regions we have seen. And this black indicates the negative trend, and gray area indicates the positive trend. So you can say that there is a big tendency for the first wet spell to start 6 days earlier and ends 2 days later. So period of the rainfall activities, which is approximately 4 days longer in recent years as compared to the other period. So that exact the same signal we can see in the onset and withdrawal dates of the monsoon as well. So these are some other factors are also there which are affecting the monsoon, like El Nino, Southern Index. So these are the global teleconnection patterns are there. We call it as a teleconnection patterns because they are not directly affecting the monsoon, but they are indirectly affecting the monsoon. So if some parameter is high in some part of the globe and this at the same time it is low in other part of the globe and they are varying synonymously, then we call it as a oscillation. So there are different oscillations are there throughout the globe, but there are few 6-7 oscillations are there which are very much important from the monsoon prediction point of view, which I have only shown you. So this is the El Nino and Southern Oscillation Index. So you can see that El Nino is nothing but the warming of the Pacific in the Western Pacific region than that of the Eastern Pacific region, and it is indicated in the form of the Nino 3 index, or also called as a Southern Oscillation Index. That is the pressure anomaly between the two stations in the Pacific Ocean. One in the Darwin over the Australia, and another is in the Tahiti island. So these are the Southern Oscillation Index and the rainfall. You can see that this Tahiti and Darwin pressures, they are how synonymously oppositely related to each other. So this index is considered as a INSO index for the monsoon period. So whenever there is a El Nino is happening, you might have seen that El Nino is there. That time all India monsoon rainfall is drastically affected. But it is not one-to-one correlation is there, because there are many years exist where even though strong El Nino was there, but the monsoon was also above normal. So here you can see that in one reference that in El Nino year, monsoon is also above normal. And in La Nina year, they are there, but there are some La Nina periods are there where monsoon is below normal. So you cannot say that there is a one-to-one correlation does exist, because there are other oscillations are also there. They are also contributing into that and modifies the relationship between the INSO and monsoon. Now, if you want to go to the weather systems, we have seen the monsoon, but in monsoon, there are the weather systems which are the major contributor for the occurrence of the rain. So we can have the different types of weather systems, wave systems, line systems, circular systems, and mesoscale systems are there, which are at different scales, different horizontal and vertical scales. They are working and giving the rainfall in different parts of the country. So in short, if you see in the Asia Pacific region, this is the different intense convection and convergence zones are there, where these elongated systems and circular systems are takes place. So you can divide it as 18 convergences are there where these type of weather systems took place during the monsoon season. Now coming to the extreme rain event, a very important part of this lecture, that how the climatic changes are affecting the extreme rain events. So in IPCC fifth assessment report, that is Intergovernmental Panel or Climate Change, I'm not going into much detail because the next speaker will speak in over that in more details, but just to give you the glance that in IPCC fifth assessment report, what happens, they are giving that because of the warming in the climate, there is a increase in the intensity of the extreme rainfall events, and it has been predicted because it has been said that because of the warming, hydrological cycle will going to be intensified, and which leads to the increase in the intensity of the extreme rain events. And then in IPCC's sixth assessment report in 2021, people have quantified it in more detailed way, that they were telling that if there is a 1 degree centigrade additional rise is there in the global temperature, then it is possible that there is a 7% increase in the intensity of the extreme rainfall. So now it is quantification is there, that how we have to limit that increase, otherwise we have to face the consequences of the extreme rise in the intensity of the rainfall. So if you see the extreme rain events, especially Himalaya, which is more vulnerable for the extreme rain events. So in subtropical Asia, means not only India, Pakistan, Nepal, China, if you see, only just after 2010, there are many events. I have just summarized how these events are happening. Major events are there, and there are so many other events are there which are unnoticed also. So there are lots of events are happening only after 2012, and not only over the Himalaya, but other parts of the country also, like Chennai event, Kerala event, then Hyderabad 2020, Maharashtra and Kerala flood 2019, and this famous flood over the Tamil Nadu in 21, Bengaluru in 22. So there are so many events are happening now in other parts of the country also. So why these extreme rain events are very difficult to study, that also we need to understand, because what happens, extreme events are randomly occurring. We have seen that in extreme rain events from 1951 to 2007, then you can see that they are happening at different parts of the country. There is no any pattern or clusters are there which you can see that extreme events happen over a particular place. But of course, there are some areas are there where extremes happens more than 3-4 times, but not more than that. And so each year new and new areas are emerging. So they are wandering phenomena. Another is they are embedded in the intense rainfall activity. So there, if there is a large scale intense rainfall is happening, then in that rainfall only some peak is happening where extreme occurs. So it is very difficult to capture that event when there is a large scale rainfall is taking place during the monsoon. So some characteristic parameters we study for the monsoon, like location between rainfall intensity, areal extent, rainwater, and duration. So all these parameters are equally important when if somebody wants to study the extreme. Space, time, and intensity are the three areas where we have to study the extremes. So when we see the extreme rainfall variation, then interannually you can see that 1 to 5 day extreme rainfall are plotted. Then you can see that in recent year there is a significant rise in the extreme rainfall intensity for not for 1 day event, but it is continued for the 5 day event as well. So, but after 5 day we could not get any signal that there is a rise in the extreme rain event. And when we see the relationship that whether the extreme rain event and duration is related, then you see that there is a second degree polynomial is the duration of the extreme and the rainfall of the extreme. And also its mean and standard deviation is also related to each other. So if you know the mean rainfall intensity, you can guess about the standard deviation, and then you can have whole distribution of a particular extreme over the particular area for the point of view. Now, I will very quickly explain one or two case studies of the extreme rain, how meteorological events are taking place. So here one event we have studied, that is the very famous 2005 months extreme rainfall event which is happening over the Mumbai. But we just remember the Mumbai. But this was the event which was the whole southern peninsula. It started from the almost you can say 23rd July it has started. It was raining heavily. So you can see that green part is that is the area where it was wet. It's completely having very heavy rainfall was happening. Then there is a 14, 24 July, 25th July, 26th July, and you can see the rainwater. How much rainwater? Rainwater means amount of rainfall and area where it is happen. So this amount of rainfall, and if you multiply it with the area, then it gives the amount of water generated during that period. So you can see that 40 billion rainwater was generated on 23rd July, then 59. Then in 25th July, only in one day, 98 BCM rainwater was generated. And on 26th July, that time when extreme event happened over the Mumbai region, that time 54 BCM rainwater was generated. But and about 48 to 54% was wet. Means you can see that this extreme was not only for the Mumbai, but whole southern peninsula was raining very heavily. So we have seen some meteorological conditions during this period, that how it is happening. So how the when the spate started, how many days spate was there, then convergence depth is there from 12 July to 20 July, then 21st July to 7 July. What are the different meteorological conditions and circulation characteristics was there, and how monsoon condition depth has increased. It can reach up to 400 HPA. That means it is up to the 67 kilometer depth monsoon intensity was there. So like that we have that this was a very event as in the history of the India. So noticeable changes also we have seen into the picture. So I'm not going into much details of this, how it has plotted and what are the parameters. But just want to show you that this green part, this is giving the warm, moist region, but the warm uh, cool regime. So, dry regime. So you can see that is the lower part of the atmosphere, and 925 is the lower part of the atmosphere. The higher kilometer is
Just a minute,
then
ma'am. Just
720
participants, it's a
kilometers.
humble request to please mute your mic.
So you can see that at how much this green part, if you see at much up into the atmosphere, that indicated that your atmosphere is very much inflated, and it is having very it is very unstable. And at upper this Tibetan and divided into three states. The picture and the whole air mass from the Tibetan high that has transported to the Southern Ocean, and because the Southern Peninsula is having very high rainfall. Now another event.
Participant, please mute your mic. It's a humble request. Please.
Ashwini ma'am, you can continue. Ashwini ma'am, you are not audible.
Ma'am, somebody is muting me anonymously.
Actually,
Because
ma'am, due to some disturbance, anyone has pressed on mute all. That's why it is happening.
Okay,
Now
okay,
you are
okay.
audible clearly.
Yeah, okay. Thank you. So you can see that there is a drastic meteorological characteristics different in the Mumbai 2005 rain event and Kedarnath 2013 rain event. So this Kedarnath 13 rain event is a classic example of the tropical extratropical interactions. So this blue area is indicated the cool, low, dry area, and green indicates the warm, dry, warm, moist area. So this is the characteristics of the tropical feature, and this is the extratropical feature. But when this extratropical feature comes over the tropical region, then there is an interaction and there is a sharp contrast is there. Then this warm, moist air can rise over this cool, low regime and can have the drastic instability takes place over that region. So we could find that 5 factors are there which are the main causes of the this extreme. One is, I say, that drastic difference between the two different regimes, cool low regime and warm low regime. And then there is a squeezing of the moist region, because you see that in the upper atmosphere this Tibetan high is splitted into the two cells. So in these two cells, what happens, whatever the air comes from the surface, then it has to rise along the slopes of the Himalaya rather than to merge with this another anticyclone, because at two places, both places anticyclones are there. So it has to rise in between. So that there is a squeezing of the moisture flow takes place from the western slopes of the Himalaya. And parallelly at lower level, low pressure area and warm area region is there. So that means there is a lifting of the moisture air is there, and at upper area there is a pumping. So we call it as a Ekman suction and Ekman pumping. So these both took place simultaneously, and it can create this anomalous and unprecedented event during 2013. So this is very classical example of the tropical extratropical interaction, and also this is very unique because this type of picture you will not get every time. So that's why I said that it is a very unique phenomena happen. Then after that also there are many extreme events happens over the Himalayan region, and more or less the picture is same, but it was not that intensified as it has happened during the Kedarnath floods. Now coming to the monitoring. So we have seen the climate change, monsoon, extremes and all other things, but we should know that how this people are studying this and how it is monitored. So there is a continuous monitoring takes place from the surface and upper air observations are there. There are different meteorological agencies are there which took observations at the surface level as well as they took throughout the atmosphere upper air observations. Then there are oceanic observations are there using ships and buoys. Then there are monitoring is there using satellite imageries and satellite bulletins. Then there is a real-time monitoring using weather radar. Then there is a people used to plot the meteorological charts in order to understand the anomalous features, and then aircraft reports are also there. And lastly, there is a numerical weather prediction models which are giving the forecast and real-time condition of different weather all across the globe. So these are some of the meteorological instruments. I'm not going into the details of that. So these are the instruments for different parameters like temperature, humidity, wind, pressure, etc. And this is automated weather station where all the sensors are actually equipped, and it can be placed in those areas where you cannot go or they are not easily approachable. So their automatic weather station plays very important role, which keep on taking the observations continuously and sending that to the systems where or data loggers. It's called as a data logger. So these observations are stored into the data loggers, and later on you can take it out, or you can through signal you can transfer also. Then there are some radio sonding instrumentations are there here. Universities also, you might have seen that there is one balloon is there, and the sensors are connected with these balloons, and this in every week or once or twice in a week, these balloons used to send up into the atmosphere, and while going, it captures the vertical profile of the atmospheric parameters, temperature, humidity, wind, and other parameters, and which is used for the real-time monitoring of the weather. So in all these meteorological instrumentations, weather radars are having its own importance. And after development of the weather radars, we can say that there is a significant advancement takes place in the meteorology, especially Doppler weather radars, which are based upon the working principle of the Doppler principle, where if anything is coming together, comes towards you or going away from you, then there is a change in the signal or frequency of the we are getting. So based upon that principle, these Doppler radars are there, and they are now installed in different parts of the country. So now there are 38 to 39 Doppler radars are already installed in different parts of the country, over the coastal regions, over Himalayan regions, and different parts to in order to understand monitoring of the cyclones or any extreme weather events over happening. Then another advancements in the meteorology takes place after the weather radars. So when the weather radars are weather satellites started, then there is a drastic changes happening, because we are getting the continuous observations from different parts of the globe, and from those areas which are not easily approachable. So if you see the India, then there is a first weather satellite, that is Kalpana 1. Kalpana 1 is the first weather satellite of the India. And in this, then afterwards, there are many satellites comes. You can see that this is satellite traffic, how much it is orbiting across the Earth. So then after, you might have heard INSAT 3D, 3DR, OceanSat. So different megatropics is also another satellite. So there are a number of satellites are there which are evolving around the Earth. That is from India, and there are other satellites are there from which are from the other countries, like GOES satellite, NOAA satellite, or your Meteosat. So different satellites are there which are keep on continuously giving the parameter information. So there are different sensors are there in that satellite. We call it as a imager. So imagers are giving the pictures of the any particular area. Then sounders are there, radiometers are there, and even radars are also there on board of the satellite. So because of that, lots of advancements now taking place, and we are getting the observations from different parts of the globe. Then the last is the weather and climate modeling. So all these observations from the surface, upper air, satellite radar, they have to combine, because ultimately we are interested in the rainfall forecasting or weather forecasting. So we have to run the weather and climate modeling models. So I am not going into detail, because there will be fully dedicated lecture will be there in the coming days on the weather and climate modeling. But in short, I say that this model means when you understand all the atmospheric processes, and if these processes are, if you present in the form of equations, and if you solve these equations, then you are getting the forecast, that is your climate model. So in short, climate model works on this principle, that if something is coming in, then what is coming in, how much is produced, how much is distracted, and how much is coming out. So at each grid point, it has been calculated for all across the globe. So in short, there are, you can see that climate model in a broader scale, you can define as a, there is a forecast model, there is a data assimilation system. So in data assimilation, you are assimilating all the data from different means, surface, upper air, satellites, as I say, oceanic, and then these, they are giving the input to the model. So they have to be in the form of the forecasting model. So which model can accept. And then there are different parameterization schemes are there, because there are lots of parameters are there which are not able to resolve in the model resolution, because there are so many mesoscale parameters are there, like cloud processes or any mesoscale process which are not resolved in the model. Because if model's resolution is suppose 10 kilometer, then you will not able to show any cloud of 1 kilometer size. So that has to be resolved in some different parameters, and then they have to be incorporated into the model. Then there is a dynamics is also there. So combinedly, all the things combine and forms the model framework and run the model. So this is very vague actual representation. In reality, the model is a very, very complex process, because all these equations which you are going to solve, they are non-linear and partial differential equations are there. So it takes hell of time and lot of computational power is required to solve these equations. So and then are two types of models are there. As I said, there is a weather model and there is a climate model. So climate model is little bit vague, which will not taken into consideration of small processes, but they are more considered large scale processes, and the processes, especially oceanic processes, which respond very late, because ocean is the area which responds very late. If something is happening in the ocean today, then it will respond after 2 months, 3 months, 4 months, or even 10 to 15 years also. So that thing also taken into consideration while running the climate models. But the weather models are there, which are generally of higher resolution scale. They take input from the climate model and run over a particular smaller area and gives you the forecast for less 10 to 15 days. But climate models can give you for prediction for the few hundreds of years ahead. So for this weather and climate modeling, nowadays there is a seamless modeling is there, because we are having the very high computational power. So one model can work for both the things, but people have started working on them. So these are some general nomenclatures of the models you might have heard in the literature, that atmosphere general circulation model, ocean general circulation model, atmosphere ocean coupled model. So, and then earth system model. This is the recent models are there. Then different agencies are giving the forecast, like ECMWF, NCEP, UK Met Office, all these Japan, they are giving the different forecast. Then there is a coupled inter-comparison projects are there, that all different climate models comes together and give the concise forecast. CMIP 5 and CMIP 6 models are there. So whenever you will going to see the climate scenario lecture, then you will come to know more about this in details. So these are some different nomenclatures are there, which are in the general use for the atmospheric models. Then, as I say, that models are having large computational power. So this high performance computing, when it comes, then it has drastically changes the forecasting ability of the is in the meteorological field. So you can have that these high performance computers are there in even in recently you might have heard in the news seen in the TV channels or newspaper that some recent supercomputer facilities are installed in India, like Airavat. Airavat has been installed in Pune, CDAC, which is the 136th rank of the supercomputer all across the globe. Then there are two more supercomputers are especially devoted for the climate modeling and weather modeling. That is Pratyush. One is in the Indian Institute of Tropical Meteorology in Pune, which is having 4 petaflop size, and another is in Mihir, which is in the Noida, NCMRW of Noida, having the 2.8 petaflop capacity. So means these facilities are there, and because of these facilities now it is much easier to incorporate more and more data into the atmosphere, and more high resolution climate models we are able to run. So now this is the forecasting range, that with all these models you can forecast into the nowcasting range, short range 2 to 3 days, then medium range 7 to 10 days, then extended range, and then long range. So different ranges are there in this forecasting thing. So coming
Sorry
to
to
the end of
disturb
this
you, ma'am.
lecture.
Yes,
Yes,
okay. 5 minutes remaining.
yes, ma'am.
Okay,
Yeah.
okay.
So ultimately, after looking over all this monsoon extreme events and climate change, you can have like summarized picture of the nexus, that how this nexus works. So we have seen that global climatic changes are takes place. There is a rise in the temperature, rise in the mean sea level pressure, retreat of the gaseous, rise in the carbon dioxide and other air pollutants, and they are affecting the monsoon variability. That we have seen that there is a weakening and westward shifting of the monsoon, declining the precipitation, especially over the central India, delays in the onset, earlier withdrawals, and then interannual and intraseasonal variabilities also takes place, and uneven distribution is also there, and then ultimately it is affecting the extremes, that rise in the trend frequency and intensity of the extremes, and then there is a decreasing trend in the frequency of the monsoon depressions that we have not discussed, but here only I will explain that there is a change in the trend in the monsoon depressions, and in the spells we have seen that prolonged dry spells are seen and intense wet spells are seen, and then more severe heat waves and tropical cyclones. So all these are working uh, and all are connected to each other. So that's why it is called a nexus, that climate change, monsoon and extremes are working together. So, and these are creating the challenges for disaster management that we have not able to miss in disaster management. I am also not going into tackle, but just I have pointed out few things that why the disaster management is so difficult, because we are not having early warning systems, those which are required that much adequate in the remote and rural areas. Then there is a poor drainage facilities there. Then coordination is one of the major important constraint. Then the India's population is also major constraint, and they resides in the those areas which are floodplain or coastal regions or Himalaya region, like that. And then there is a rise in the natural disasters, and also some other policy issues that we are not investing sufficiently into the infrastructure training and community awareness and technological different challenges are there for the disaster management. So ultimately we have to work on three respect technological solutions. We have to have technological solutions in the form of models, in the form of early warning systems or monitoring systems to understand your physical processes from the research. And then we need policy interventions in different places. We need more investment. And then we also have some mitigation strategies, that we should have resilient infrastructure, maybe rainwater harvesting, afforestation and awareness activity, drainage system. So in all three aspects, when we will work together, then only we will able to cope up the climate change and monsoon and extreme rain event vagaries which we are already experiencing. So thank you so much. I think I'm well within the time now.
Yes. Thank you, ma'am. Thank you so much. Participants, any questions you can ask?
Very good evening.
Yes, yes, please.
So, myself, Professor Dr. Sandeep Patil from Bharati Women Engineering College, Pune. First of all,
yes,
I
sir.
appreciate the great content delivered by Ashwini Ranade, madam. It was very highly informative, and it has dealt with all the evolution right from the beginning, methodology, and your session has enlightened all the participants and the people about the environment, ecology, and its importance. All the disaster happened in depth, the technical aspect of this disasters and how we can. So thank you. It is really appreciable and very important session for all of us, which enlighten us about the environment, ecological, and its importance and how we can contribute. So thank you so much for very invaluable information about this topic. I
Yes,
would like to
thank you for your nice words.
I would like to know how other discipline faculties or researchers or students can contribute in this uh, environment related problems or projects, etc. Please guide us.
Yes, thank you so much.
Hello.
Hi, yes, ma'am. Sir, Patil sir, can you repeat your question?
Yes, I would like to know that how other discipline, faculty, students, researchers could contribute or collaboratively work for this environmental related problems so that the spreading of awareness among all, because environment is for all, ecology is for all, and each one, every human being and living species should contribute for the sustainability of it. So how other disciplinary people or elements can contribute or collaborate to solve certain challenges in the environment?
Yes, sir. It's a very relevant question, actually. As I said in my talk also, that climate change is not like a subject. It is a multidisciplinary or interdisciplinary subject where all different sorts of people have to come together and work on that. So even if you are working on the monsoon and extreme event, there are a number of things through which we can contribute. Means, for example, as you all are from the different engineering backgrounds, so we really need the technologists who can work on that, especially if the person who are doing computer sciences, then we really need those people who can contribute into the weather and climate modeling advancements, writing codes for that, and try to understand the processes and write in the forms of equations and to solve it. So for the computer science, AI and ML now recent advanced in the weather and climate aspect also. So we really need AI/ML people also in order to work in this subject area. Then we need also mathematicians who can write the processes in the form of equations. Try to give the solutions for these nonlinear equations in better way, how to solve that. And there are many different aspects are there. Even the technologies we need, if you say the water resources, we really need those resilient interventions and infrastructure so that we can store the water. Whatever the water we are getting, as I said, that in one day, if you are getting the 98 billion cubic meter of rainwater, do we have that technology that can store that much of rainwater together? So we don't have. So stormwater storage is also one of the important aspects where civil engineers can work on that and can suggest some solutions which can be used in the water resources sector. And so there are different sectors are there. So I said that in every aspect, climate change is there. In everywhere, it is affecting. So we cannot say that climate change is the topic which should only meteorologists or hydrologists or those environmental should study. But in every aspect, it is there, and each specialization is required. So I should say that 16 subjects are required. I said 16 subjects are required, which can give the understanding of the climate and where we can adapt the climate and then how to mitigate the climate. So the all things are required everywhere. Chemistry people are required. Those who work on the atmospheric chemistry can give the solutions for the air pollution and give new technologies for that. So if we want to reduce the GHG emissions, then how we can develop the our appliances such that which will not emit that, or even automobile people are there, those who can work on that, so that this vehicular pollution can be reduced in some other way. We can reduce the CO2 and all other things. So I can say that in technology, all engineers are required along with the scientists. So all engineers, scientists, architectures, they should combine, and social scientists also are required so that people make aware about the climate change and they should adopt the thing that whatever the climate we are experiencing, then they can adapt it accordingly. So everywhere, all the people are required all across the sectors. So they can contribute in on the way in that.
Thank
I
you.
think
Thank
up to some extent I can explain this.
Yes, thank you so much for your suggestions, and all the disciplines can contribute because the
Yes,
nature it's the multidisciplinary. It is we the human being made it disciplinary and isolated and working in isolated compartment. I think we have to
yes,
forward and join hands to collaborate with together with
yes,
such
yes,
organization like And we are fortunate enough to have that we have IMD center in Pune. So we will try
Yes.
to approach them, and with their collaboration and support, we will definitely plan certain assignment tasks and projects where we can find out how we can contribute with them. So thank you so much once again for your insightful and very enlightening session. Thank you so much.
Okay. Participants, any other questions you want to ask to ma'am? No questions? Okay. So thank you, ma'am. On behalf of Bharati Vidyapeeth College of Engineering for Women, Pune, I extend my heartfelt gratitude to our esteemed speaker, Dr. Ashwini Ranade, ma'am,
Hello.
for delivering such a
Yes,
thought-provoking and enriching session. Your expertise and insight have been truly valuable to all of us. I also thank all the participants for their active engagement and enthusiasm throughout the session. Kindly please join the next session immediately after this. Thank you, ma'am. Thank you so much.
thank you.
Thank you
Thank you
so
so
much.
much. Thank you so much for listening me patiently. Thank you so much.
Thank you, Ashwini ma'am.
Thank you. Thank you, Sonali ma'am. Next speaker is
Our
available.
next session. Yes, ma'am.
Sunil sir, are you there?
As ma'am has already said, I'm working as scientist, Dean Center for Cryosphere and Climate Change Studies. I've heard part of Dr. Ashwini Ranade's lecture, and she has given some introduction about what weather and climate is, and what are climate models. Just give you this lecture in my presentation. It will be basically about all the basics about what weather climate is, what are the weather climate data is, where do you get those data from. I will quickly skim through all this information, and then I'll give you an introduction about climate models, what are GCMs, what is IPCC, what are CMIP 6, what is climate model intercomparison project is all about, and then what are SSPs, shared socio-economic pathways. I'm sure most of you are aware of it. And then I'll also talk about the downscaling part, a little bit of everything actually. And then I'll talk about the impact assessment, what can be done, and I'll give you some overview of what my results are from impact assessment studies. So this is the overview of all the presentation. Before going further, sorry, yeah. So before we start talk about climate change or climate variability, or if we even if we want to do the climate change impact assessment studies, we should know what is the difference between the basic difference between weather and climate. I'm sure Dr. Ashwini has already mentioned this, but just a quick review. The weather is the state of atmosphere at a specific time and place, including temperature, humidity, precipitation, and wind. So it is mostly about what is happening at present, today, yesterday, or something like that, at a shorter time period. I feel understanding the difference between weather and climate is very important, because when I started doing research in climate change, I didn't really understand the exact difference between weather and climate. So I just thought this would be a quick review of this. Coming to climate, what the climate is, the average weather conditions of a place over a long period, typically 30 years or more. So when we have an average climate of longer period at a particular place, we can call that a climate of that region. When you are asking about what is the temperature today, you say what is weather like today. So that is the difference. What is the climate? If you want to know about a particular region, what is the average climate in that region, you ask for climate. Or if you are asking for the conditions today, you ask for weather. So as I mentioned, it is the short term or changes frequently is called short term. Weather is short term and it changes frequently. As when you say daily, monthly, or annually, it is a weather. When you're talking about climate, it's a long term trend. annual trends for a past 30 or 50 years. So once you understand appreciate the difference between weather and climate, the next thing you should understand is what is the difference between climate variability and climate change. This is also very important. What is climate variability and what is climate change? Climate variability looks at the changes that occurs within a smaller time frame. So when we are looking at when you're talking about diurnal changes, that is the changes in temperature in a day, or how the temperature is changing in a month or a season or in a year, we call it as a climate variability. Again, this is a short-term variability. When we talk about short-term, then we call it a climate variability. And then climate change comes into picture when you're considering changes that is occurring over a longer period of time, typically over decades, multiple decades. When I said talking about climate, there is a 30-year period or more than that. So when you're talking about a change in the climate data, we call it as a climate change. Typically, what does a climate change represent? Any systematic change in the long-term statistics of climatic elements. What are all the climatic elements? We look at a typical meteorological station, be it a temperature, pressure, wind speed, relative humidity, all the basic meteorological variables, how they are changing over a longer period of time, we call it a climate change. So the definition here, as I mentioned, any systematic change in the long-term statistics of climate elements such as temperature, pressure, or winds sustained over several decades or longer. So this is the picture you can see here. This is for the past around 100, 150 years or so, how the temperature has changed. These are the pictures that you might have seen every time you talk about climate change or climate variability. If you have gone through IPCC reports, you might have come across such pictures a long time. So basically what it is saying is up to 1940 or 1950, the average temperature is within certain limits, but after that it has gone beyond the limits and it's keeping on increasing. So this is basically the increase in temperature. So to be able to understand or appreciate what is climate variability or climate change, you need climate data. So what is climate data? I'm sure all of you are aware of the data that captures long-term trends, variability, and averages of atmospheric, oceanic, and terrestrial systems. Importance of climate data is essential for understanding climate change, monitoring trends, and planning mitigation and adaptation strategies. Nowadays, because of the increased frequency of extreme events, be it floods or droughts, we should be able to appreciate what has happened in the past and how it is affecting the future. If there are any such instances in the past. So nowadays there are some instances, there are some floods where the IMD or the ministry releases a report saying that this is a 1 in a 100-year flood, or this is a 1 in a 100-year coldest day. So you have the historical data based on which you identify what has happened to the today's weather or climate. There are types of data. This is the basic observed data, remote sensing data, interpolated data, reanalysis data sets, model data sets. Here, observed data, as you are all aware, I don't have to go through in detail. This is a ground-based measurements. Remote sensing data, again, everyone is aware of satellite information or remotely observed data. I'll just give you a quickly skim through these types of data in a later slides. What is interpolated data, what is reanalysis data, what is model data. These are the three data sets that a climate change scientist or policy maker should appreciate. What are all these three different types of data sets, because they become very important when you are doing a climate change impact assessment studies. The sources of climate data, ground-based observation. As you are all aware, every institute nowadays has a meteorological station. As ma'am has already mentioned about ocean buoys and radio sondes, I'll give you a quick pictorial presentation of all these observation types. And then satellite observations, you have known generalized global precipitation model, MODIS dataset, Landsat, Sentinel. You use all these datasets for understanding the DEM of the globe or LULC data, of the globe. We use all these data sets. These are the satellite observations. Then we have global or regional climate networks. Like these are the gridded data sets that are provided by the global organizations. Even we have IMD dataset, WMO, World Meteorological Organization, NOAA is National Oceanic Atmospheric Academy, and then we have ECMWF and other national agencies like IMD, as I mentioned. Then we also have climate models, regional and global climate models. We have that information as well. This is a basic ground-based observation site, typical meteorological observatory. I think we all have idea about this. We have different instruments scattered across a land where different observations are made. Like here we have a precipitation data being collected. We have humidity information collected, pan evaporation information. Then we have temperature, and then number of sunshine hours kind of thing. Other than this, nowadays everyone is using automatic weather station. This is a typical automatic weather station. Not every AWS has all these sensors, but there are selected sensors that you install on the automatic weather station, where the data is collected and then transmitted to where you are sitting on your system. You install this instrument at a particular place, and all the information gathered from that collected by that instrument is transmitted to your system. Like here you can see different sensors, like it is giving a wind direction. We have a pyrometer, we have wind speed sensor, air temperature. There are different sensors here, and it is also collecting information about the pH. There is also sensor here, soil temperature, moisture, and all. A tipping bucket, rain gauge, all this information is collected. It is also stored here, and it is also transmitted immediately. In addition to that, madam, this is a ocean buoys. It collects information on the ocean surface. There are different sensors installed on it. It is the ocean buoy is anchored to the surface of the ocean, and then it floats on the surface of the ocean. It has different sensors. It has solar panels which actually power the sensors to extract the information and then transmit the data. Wave sensors, it has wave sensors, water current profiles. So this is a type of instrument that is in the ocean. Then ma'am has mentioned about radio sondes, where you have sensors tied to a balloon and then left it into the atmosphere. During its upward movement and downward movement, it gathers information, and then the information is transmitted to the system. Other than that, we have a remote sensing satellite. This is a group of satellites. This is a group of satellites providing data to a global precipitation model. This is a constellation of satellites. So this is one kind of collecting data. In addition to that, nowadays, if you want to collect information for a particular region, earlier one, it is giving a global data set, but then if you want a more finely observed data for your particular region of interest, then you make use of drones. So this is a weather drone where it has lot of sensors fixed to it. So so these weather drones can be used to get the remote sense. So these are challenges of observed climate data. There are spatial gaps. This is limited coverage of remote areas like oceans and polar regions. So you cannot observe each and every point on the land and also on the ocean or in the atmosphere. So there is a spatial gap when you're talking about observed climate data. Instrumental limitations, variability in data quality due to aging or faulty sensors. Sometimes sensors, they get if you are installing a sensor in a remote location, then you may not be able to quickly repair it or something. So there are limitations regarding that, and there is also uncertainty about error associated with the instrument. And then data accessibility, and again, if your instrument is remotely located, then you don't have enough access to that. Then standardization issues. Each instrument measures particular variable in a different way. So there are different instruments, same sensor measuring temperature as 10 degrees, other sensor might give it as 9 degrees or something. So there are some standardization issues, so that can be sorted out. And then comes the interpolated graded data sets. Because I mentioned one of the disadvantages of observed data is the spatial irregularity. So there are spatial gaps. To fulfill that spatial gaps, we have interpolated graded data sets. Observations from irregularly spaced points are used to estimate values at the grid points using mathematical techniques. We use different interpolation methods. I have listed out some here. Linear interpolation, Kriging, spine interpolation, or inverse distance weighing. So there are different interpolation techniques that you use wherever the points, at whatever location you have the data, use that information, and then you use some kind of interpolation technique to identify or to estimate the value at a grid of your grid that you design. So this is an interpolated data set. We have a very popular interpolated data set we have is from IMD for temperature and precipitation, but they are at different resolutions. For temperature it is at 25 kilometers, and for temperature it is at, for precipitation is at 25 kilometers, and for temperature is at 100 kilometers. This is available from 1951 to present. It is available for free. Whoever is willing to use the data, you can download it from their website. There are different certain procedures to follow, and then you can download that data. So this is a very important data set where, for example, as I said, it also depends upon the density of the instruments you have in a particular region. For example, in most of the mainland, you have enough density of instruments, but then you have in the northern Himalayan region or in the western Ghats region, you don't have enough instruments to actually correlate with the observed data set. But this is a good data set to start with. And then there are other data sets, interpolated graded data sets, like this one is CHIRPS data set, Climate Hazard Center from UC, University of California, Santa Barbara. So this data set is also available. This is available at 5 kilometer resolution, but only thing is this is available only for precipitation data set from 1981 to present data set. So this is also one data set that you can use. I have given the links. I have shared the presentation with you. So all the information that I am talking, if it is not clear, you can also go through the presentation. And the link for the data sets are also added in the slides. So you can access the data set from the links. Then there are challenges as well in interpolated data sets. Again, the spatial, the irregularity in the spatial representation becomes an issue. Reduced reliability and interpolated values in data scarce regions, spatial and temporal resolution limitations. Fine scale climate features like local storms may not be smoothed out. Sometimes, as I said, in a hilly region, you cannot directly use a linear interpolation method. So there are such limitations, spatial and temporal resolution. And then you have uncertainty in input data. Uncertainty increases, especially in regions with few data points. So when you have very few data points, but then you are trying to interpolate it for the larger grid, then you have certain uncertainty issues. And then climate extremes representation. So when you're smoothing out, when you're using some interpolation method, the extreme might be smoothed out. And then lack of standardization, again, there are different methods used for different graded data sets. So there is the standardization issue there. Then you also have a reanalysis data sets. Reanalysis data set. So as I said, we have looked at observed data sets. We have interpolated data sets. Now this is a reanalysis data set. What is reanalysis is that it is a data assimilation process combining observations and model outputs to create a consistent and comprehensive global data set. So you're having a set of observation data from wherever you get it, from the weather stations or from a remotely observed data sets. You have all that collection of data sets, and then you also have a climate model. So you give those observed data as input data as a boundary condition to the climate model, and then you run the model, you get some kind of reanalyzed data. Importance is provides spatially and temporally consistent records of understanding past climate, studying trends, and initializing weather and climate models. So it is one important data set that is used mostly for what you call bias correction methods, or for statistically downscaling the climate change model information. We use reanalysis data sets. So there are different reanalysis data sets. What are the Data sources used in creating a reanalysis data set. It is again, I mentioned ground-based observation. We have satellite data, weather balloons, ships, and buoy. So you have all these information, then you apply some kind of data assimilation, and you use that information in a modeling area. Ingest raw observations into climate models using statistical techniques. Dynamical models fill gaps and maintain consistency. So a dynamical climate model is used, and then the observations are used as a boundary conditions to run the dynamical model. Spatio-temporally consistent data sets covering multiple climate variables. So you can run it for different climatic variables, and then you can have different data sets of these meteorological or climatic variables. So there are key reanalysis datasets. ERA5 is most commonly used. It's a ECMWF reanalysis datasets. ECMWF is nothing but European Center for Medium Range Weather Forecast. So that model is used, and then boundary conditions are used from globally, and then it is a global datasets. Resolution is about 31 kilometers, and then it is available from 1950. Then there is other reanalysis data from NASA. It's called MERA. The full form is Modern Era Retrospective Analysis for Research and Application. This is the second phase, and it's from 1950 to present is available. Resolution is about 50 kilometers. Other one is available from NCEP NCAR reanalysis dataset. It's National Center for Environmental Prediction or National Center for Atmospheric Research. They have a resolution of 200 kilometers from 1950 to present. So these are some of the reanalysis datasets available that you can use for statistical downscaling or bias correction. So these are, I think, the websites or the home pages. From these pictures are from the home pages of the websites. This is a comparison. There are different data sets, ERA5, MERA2, JRA. This is from Japan, CFSR, NCEP, NCAR. There are different data sets. What is the period of data available? What is the spatial resolution? What are the key strengths, and where you can apply those data sets? This is a comparison table that you can use. And then challenges again in the analysis data sets. Uncertainty in older data, because in olden period like in 1900s or 18th century or something like that, we have very limited data, and then the quality of observed data is very poor. So that can cause some uncertainty in the reanalyzed data or the boundary condition that we provide to the dynamically climate model. Then we have some bias in the models. Model assumptions can introduce systematic errors. Sparse observational inputs. Observational inputs, as I mentioned, they cannot be regularly located. So we have some gaps in that. Then we have resolution limitations. May not resolve local climate phenomena like small scale storms. As I mentioned, the lowest we have seen in the reanalyzed data set is 30 kilometer resolution. We don't have much lower than that. So there are local scale phenomena cannot be identified by that model at 30 kilometer resolution. So then we come across the modeled climate data sets. What are modeled climate data sets? These are outputs from climate models that simulate the Earth's climate using physical, chemical, and biological processes. So you try to mathematically represent all these processes, physical, chemical, and biological processes, and then you run the model, you get some kind of output. That is a model climate data sets. There are different assumptions made in this. There are different boundary and initial conditions provided to the model. So there is a lot of scope for uncertainty entering into the output from a global climate model. So what are the key features? It provides predictions, hintcasts, and projections for past, present, and future climate conditions. So what is a prediction is for the shorter time period in the future. What is hintcast is we can run the model for the already past period, like in the past, and then projections is for the longer future period. We can run the climate model and then project the climate into the future. Why use modeled climate data? Advantages over observations. We have fill spatial and temporal gaps in observations. So there are some gaps, as we discussed earlier. There are gaps in observation data. We can that can be filled using output from a global climate model. So and then we provide consistent data sets for regions with sparse data. Example, oceans and polar regions. So in that regions also we have some consistent data sets. The purpose is to understanding climate processes and making predictions about future climate scenarios, supporting policy and adaptation strategies. So, because as I've already mentioned, we don't have enough observation data to understand how the climate, to understand the climatic processes. Uh, so these model simulated output can help us understand how the actual climate is behaving, and it can also help us making predictions into the future climate. Then also it also supports the policy and adaptation strategies. There are types of models. I think Madam has already talked about the types of models. Weather forecast models is for short-term atmospheric predictions for 1 to 14 days. WRF model is weather forecast model, and then we have climate models, long-term simulations, year to centuries. We also have global climate models. Then we have regional climate models depending on the spatial resolution. We call it global or regional climate models. Then we have Earth system models, integrated models including atmosphere, ocean, land, and biosphere. Other than that, what is a climate model? Any model, when we talk about it, is a simplified description or a simplified representation of reality. As the definition says, a simplified description, especially a mathematical one of a system or process to assist calculations and predictions. So when we're talking about physical model, we say it is a replica of reality. Here we are talking about mathematical model, so it is a simplified description using some kind of mathematical equations, all right, of a system or process to assist calculations. This is a climate model. Climate models, mathematical representation of Earth's climate system, including the atmosphere, oceans, land surface, and ice. Why do we need climate models? Again, to create an understanding of the climatic process. We have seen this in the earlier slide also, to understand past, present, and future climatic conditions, plausible scenarios, and to plan for the future. So this becomes a very important climate model, becomes very important to make adaptation strategies into the future, and to plan in water management, for example, when you talk about hydrology in the future. So the types of climate models, we have energy balance model. This is a one-dimensional model predicting the variation of the surface, strictly sea level temperature, as a function of energy balance of the Earth with latitude. This is a simple Earth balance model. These are the first generation models used to investigate sensitivity of climate systems to external changes and interpret results from complex models. Then we have radiative convective models. These are again one-dimensional with respect to altitude and compute the vertical, usually globally averaged temperature profile by explicitly modeling of radiative processes and convective adjustment, which reestablishes a predetermined lapse rate. Radiative convective climate models study the effects of changing atmospheric composition and investigate likely relative influences of different external and internal forcings. And then we go to the statistical dynamic model. These are the generation of models, how they have evolved. These are two-dimensional models that deal explicitly with surface processes and dynamics in a generally averaged framework and have vertically resolved atmosphere. Statistically dynamic models used to make simulations of chemistry and stratosphere and mesosphere. And then we came to the global circulation models, where the three-dimensional nature of atmosphere and ocean is incorporated. Vertical resolution is generally finer than horizontal resolution, includes AGCM, atmospheric global circulation models, OGCM, oceanic global circulation. Earlier we used to have two different models, atmospheric global circulation models, oceanic global circulation models, and then the coupled, then we started coupling different models together, and then we have atmospheric ocean global circulation model. Now we have different spheres of models clubbed together. I'll see how that has evolved in the I think next slide or so. The resulting set of coupled non-linear equations are solved at each grid point using numerical techniques that use time step approach. As I mentioned, this is the model there are different processes are represented as mathematical equations, and then that nonlinear equations are solved at each and every grid. So we develop a grid, and then that information is solved at each and every grid using some numerical technique. Atmospheric grids points are 2 to 5 degrees with time steps 20 to 30 minutes. Vertical resolution is 6 to 50 levels, 20 being typical. So there are grid points. Spatial. This is nothing but the spatial resolution, 2 degree to 5 degree with a time step of 20 to 30 minute interval, temporal time scale. This actually shows the development of climate models. Started in mid 1970s, where we only had atmospheric climate model, and then in mid 1980s we have atmosphere and land surface models. Then we have oceanic climate model in early 90s, 1990s, and then late 1990s we have added chemistry into it, and then we had sulfate and aerosol model. Then we have carbon model added in 2000s, about 2000, I mean late 1990s, and then in 2000s we have vegetation and atmospheric chemistry improved, and then in 2010s we have different hydrological model is also incorporated, sometimes land ice model. So this is how the climate models have evolved in the past 50 or 60 years. This is actually a pictorial representation I got from one of the IPCC reports. What is IPCC? We'll discuss it later on. Sources of modeled climate data. There are different sources. We have climate model data information is available. The first and foremost is the global climate models, or the GCMs that we all commonly know them. This is available from CMIP. This is a coupled model intercomparison project, which I'll discuss details later on. So this model intercomparison project will provide you some model output data, and then we also have some analysis done from IPCC assessment reports. Sorry. Then we have regional climate models.
It's a humble request to all participants. Please mute yourself.
Okay. I thought someone was asking a question. Sorry. Regional climate models. Then we have a coordinated regional downscaling experiment where the global climate models are downscaled to a particular region of interest. The globe is divided into different regions: Southeast Asia, or North America, South America, different regions. And then the coordinated regional downscaling experiment was conducted using CMIP 5 observations. So that is where you have a regional climate models as well. Operational weather models. We have weather models at a national level, like NCMRWF. It is a national center for medium range weather forecast. This is for India. Then we have European Center for medium range weather forecast for Europe. National Ocean Atmospheric Administration. This is for US. Then we also have UK Met Office. This is again for United Kingdom. There are different weather models across the globe that are doing the weather forecasting for a shorter range. Just 1 second, please. I'm getting a call. Sorry for that. So these are different sources of modeled climate data, and when we talk about climate change, one thing we frequently hear about is Intergovernmental Panel on Climate Change. This is an apex organization for assessing climate change science, impacts, adaptation, and mitigation. It synthesizes knowledge from scientific literature and provides relevant reports. These are very valuable reports if you want to know what is happening across the globe in the context of climate change and different impact assessments. Then these are the reports that are released. Now the latest set of reports are the assessment report 6, sixth assessment report. This is there are 3 working groups, and 3 working groups release 3 different reports. The first report talks about the physical science basis of climate change. So how what is the science behind a climate model that over the past based on which the current set of reports are prepared. So this discusses about the physical science basis of climate change, that is working group 1. Then working group 2 is talks about the impacts, adaptation and vulnerability. The research conducted on impacts of climate change and what are all the vulnerabilities of changing climate or adaptation strategies adopted across the globe based on the literature prepared. The review is conducted, and then a summary is circulated using a working group 2. Then about the mitigation of climate change, what are all the policies that can be taken on, what are all the strategies that you can adopt to mitigate the changing climate, that is discussed in working group 3. So there are the 3 different working groups, and then there are 3 different reports, and then summarizing all the output from CNIPSIS, there is a summary report also that is in short. You can discuss it, browse through it and get a good understanding of the changing climate research over the past few years. This is a schematic representation of IPCC global climate model. This is a schematic for global atmospheric model. This you have vertical representation. The atmosphere is represented in, as I mentioned earlier, in approximately 20 vertical layers, as you can see here. And then spatially, grid spacing, you can see in horizontal, it's around 100 to 250 kilometers spatial representation. Starting from poles it is smaller, and then at the equator and all it keeps increasing. And then vertical resolution is about 1 kilometer, and varying distances as you go up. And as I mentioned, there are approximately 20 layers on an average vertically it is represented, and then ocean is represented at 100-meter resolution. Okay, this is how typical. And then once you have IPCC, as I mentioned, IPCC it synthesizes all the information, and then it releases reports for review of the research community. So what is supporting IPCC is a coupled model intercomparison project. It is organized or managed by World Climate Research Program, if some of you are aware of. World Climate Research Program. It is a coordinated international effort to compare and improve coupled climate models. As you are aware, there are climate models developed by different organizations from different countries. There are around, for example, in CNIP6, we have around 36 climate models that are part of coupled model intercomparison project. So all these 30 models are developed by different research organizations from across the globe. So what coupled model intercomparison project does is it collects data from all these informations. It tries. So you have to follow certain criteria, and there are certain criteria to be qualified to be considered into coupled model intercomparison project. So so this, as I mentioned, this is a coordinated effort to compare and improve coupled climate models. So the objective of the coupled model intercomparison project is to better understand past, present, and future climate changes arising from natural unforced variability or in response to changes in radiative forcing in multimodal context. So this is the basic objective of CNIP. So it helps you to understand the past, helps you to understand the present, and then future climate changes arising at different climatic conditions. Objectives of CNIP, if you go further, it evaluates the model performance, compares models against historical observations. So it compares, it helps to compare the historical and the projected information, understand climate feedback. So there is a climate feedback between atmosphere, ocean, land, and cryosphere, how they're interacting. It helps you understand that. And then it provides projections. It simulates future climate scenarios under different socio-economic pathways. Earlier we have A1, A2, B1, B2 scenarios, if you are all aware. And then we have representative concentration pathways, that is called RCPs, and then a modified version of RCPs is a socio-economic pathways, where we are considering the developments in socio-economic developments. I mean the changes in socio-economic developments, and then that are summarized as a scenario to the model to be done. And then the observations collected from across the globe, it helps inform IPCC reports and then global climate negotiations. So all the information from the CMIP will help preparing the IPCC reports. So what is this is the basic evolution of CMIP, coupled model intercomparison project. Initially, it started in 1995, that is CMIP 5. I don't remember how many models were there back then, initial phase of the model intercomparison. And then we have CMIP 3 in 2007. CMIP 2 was not very popular. And then we have input from CMIP 3 provided input for IPCC AR4, the fourth assessment report, focused on climate projections. That is when it started becoming more and more popular. So from fourth assessment report, before that we have AR3 also, the third assessment report, and then we have CMIP 5 in 2013, basis for IPCC AR5, the one before the current assessment report, ARE assessment report. This in CMIP 5, the RCPs were introduced representative concentration pathways, which are the basis for running the climate models. And then we have more detailed scenarios in 2000 from 2019 to present. We have CMIP 6. These are called shared socio-economic pathways. I'll give you an overview in the next few slides. Then what is CMIP 6? It's the sixth phase of coupled model intercomparison project under World Climate Research Program. It's a framework for evaluating and improving climate models globally. Objective is to understand past, present, and future climate dynamics. These are the basic objectives that I've already discussed, and this is the sixth phase of the coupled model intercomparison projects. So key features of CMIP 6, what are the most important thing that you should consider is it has high resolution models, better than the previous models, improved spatial and temporally also. It has a much better resolution compared to the previous models. Focus on Earth system interactions. So it has more other spheres of the Earth that are included. Biogeochemical cycles and aerosols are also included into the latest set of models. So it has it includes biogeochemical cycles and aerosols. Then we have scenario-based projections, incorporates shared socio-economic pathways. So based on SSPs, we have projections. Then we have diverse experiments, tailored model intercomparison projects for specific studies. That I'll give you in the next slide. What are tailor-made intercomparison projects? As you can see, this is the structure of CMIP 6. We have a core diagnostic evaluation and characterization of climate. That is the model. That is the core of the CMIP 6. Then we have historical simulations from 1850 to present. The models are evaluated based on the historical simulations. Then we have scenario MIP, future climate projections under different SSPs. So this is the scenario MIP is what this is the this is what we are talking about, scenarios, different based on different SSPs. Then we also have a specialized model intercomparison process depending on what sector you want to use. Like LUMIP, this is a land use model intercomparison process. Different types of land uses are considered, and then you compare that models. And then different types of carbon emissions are considered, and then we have that kind of C4 MIP model intercomparison project. Then we have aerosol and chemistry models, different combinations of that. We have chemistry aerosol model intercomparison project. Similarly, we have paleo observations to compare the models, that is paleo model intercomparison. Similarly, you can see there are different sectors in this picture and this structure of CMIP 6. But basically, when we're talking about impact assessment, we go for scenario model intercomparison projects, CMIP SMIP. So we get the observations, I mean, whatever the data sets are available from scenario MIP, and then we use that information to do the impact assessment. Then it is the, as I mentioned earlier, we had emission scenario, special report on emission scenarios, different kinds of emission scenarios, A1, B1, A2, B2, combinations of different things, if some of you are aware of. And then after that, we have moved to representation concentration pathways, depending on how the changes will be in the in controlling the emissions so there are different scenarios in RCPs, and then we have SSPs, so shared socio-economic pathways, scenarios combining greenhouse gas emissions with socio-economic assumptions, how the socio-economic changes will happen in the future. So key scenarios is SSP 1, 1.9, SSP 2, 4.5, SSP 5, 8.5. SSP 1.9 is ambitious mitigation scenario. So we're trying to curtail all the emissions and then how the climate will be in the future. So we're assuming that there will be emissions curtailed and very ambitious, and then the model is run and we have certain set of projections. And then 8.5 is the high emission, so we let it run as it is. We let the emissions keep on increasing at the same scale, and then we let the model run. We have another set of projections, and then we have in between those two we have an intermediate scenario. And these are shared socio-economic pathways: SSP1, SSP2, SSP3, SSP4, and SSP5. You can read through it. Different between SSP1 and SSP5, as I mentioned here. So between these two, there are different scenarios. You can sustainability, that is the most ambitious one. Then the middle of the road, it is called regional rivalry, inequality, fossil fuel development. So these are the different scenario pathways, right? CMIP6 data sets, where you can get that data. So the raw data sets from CMIP6 can be obtained from this particular website. So for different variables, different set of initial and boundary conditions, the models are run. So all the amount of information you can access from this website. The CMIP6 data sets are available from here. So there are particular procedures that you have to follow before you can download the data, and there are different runs of the model. So you have to make sure you have to have a clear idea on what model and what variable, what run you're trying to download the data for, and at what time scale. So you can browse through this website. And then this is a typical representation of how the global output will be. As you can see, the north and south, there is a blue color which is indicating the cold. This is for a temperature which is colder temperatures, whereas in the equator and tropical region you have a little bit warmer temperature. It's not about that I'm trying to show here. It is about the kind of the resolution. As you can see, for India, there are only like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are a handful of pixels or the grids that are representing India here. But you know how diversified the climate in India is. So here what I'm trying to show is, if you're using the global output model at this spatial resolution, can you really depict the actual weather or climate of India? So that is very questionable. So this is where the picture of downscaling comes in. So just want to give you an overview of what is downscaling, why there is a need for downscaling. So so this is a real world, as you can, this is a globe pictorially, and then we are doing some kind of observations, but they're not regularly spaced. This is for a European continent. They're different. The dots represent the meteorologically observed stations. At some stations you don't have any data. There are white spots. There are sparsely spaced. There is a lot of gaps, and sometimes there is densely spaced. As you can see, there are dense. So there are the point observations are not regularly spaced. And then you have gridded observed based products, remote sensing data that I have talked about. You have at a different pixel you have information. for a regularly gridded data sets. The gridded observation-based products, interpolated data sets for that matter, as I mentioned, IMD. But then the model world, the globe is represented by different by a big supercomputer, and then the world is spatially represented as a grid. As you can see the map. This is the same region. How this whole of European continent is represented by grid cells in this picture. Right. So this is a very high resolution coarse resolution model. Then you want to bring this model to this pixel size, and at least try you make an attempt to bring from this pixel size to a very finer pixel size. So you want what so to do that, what you do is called downscaling. So you want to bring the coarser grid scale to a finer grid scale is called downscaling. So why downscaling is needed? Downscaling is needed. There are, as I mentioned, there are GCM outputs, insufficient spatial and temporal resolution. Results in insufficient representation of, for example, orography and land surface characteristics. For example, if you see this area, like this particular grid, as you can see, is represented by a larger grid, the topography, vegetation, hydrology. Right? So this is a small portion, but then that is represented by the coarser grid. So this is some of the finer the local phenomena that happens at a finer grid scale may not be represented here. The amount of change in temperature in this region, as you can see here, the variability is very is not clear. The spatial variability. It says it's hot in here. Let's assume it's a temperature representation. The red means hot, and then yellow and relatively less hotter. So the insufficient results in insufficient representation or orography and land surface characteristics. Consequent loss of some of characteristics which may have important influence on regional climate. So there are some characteristics we want to we may miss during the representation of a mathematical model at a coarser grid. Methodology to derive more detailed regional and site scenarios of climate change for impact studies. So we want a detailed information at a finer grid scale to be able to understand or appreciate the hydrology or regional phenomena. So, and then designed to bridge the gap between information that the climate modeling community can currently provide and that required by the impact research community. If I am a person from a policy maker, I want to know whether the flow at my observatory will increase or decrease. But then, or at my particular city, will it increase or decrease? I want to know that. But then the global climate says the whole state of Andhra Pradesh or whole state of Uttarakhand, the temperature will increase or the temperature will decrease. But you don't know whether it will increase at my city or not. So to do that, you have to do some kind of downscaling. There are different approaches that you can adopt to identify a temperature or precipitation at a region of interest. So for downscaling, there are different techniques. As I mentioned, there are two types of downscaling: statistical and dynamic downscaling. Dynamic downscale is more of creating or generating a climate model, a global climate model at a regional scale. So dynamic downscaling requires running high resolution climate models on a regional subdomain using observational data or low resolution climate model output as a boundary condition. So what we do is we create a climate model for the region of interest. Similar, use all the physical, represent all the physical biological processes using mathematical equation at a finer spatial resolution, and then you use the output from the global climate model as a boundary condition. You run that regional climate model. So these models use physical principles to reproduce local climates but are computationally intensive. It needs a lot of computational resources, and also it takes a lot of time to run a particular for a particular time period or for a particular region. So there are disadvantages associated with it, but it is most accurate compared to the statistical downscaling. There are advantages to statistical downscaling, which I'll be talking in the next slide. What is the statistical downscaling is? But then dynamic downscaling is similar to constructing a new climate model for the region of interest. And then comes to the statistical downscaling. The idea of statistical downscaling consists in using the observed relationship between large-scale circulation and the local climates to set up statistical models that could translate anomalies of the large-scale flow into anomalies of some local climate variable. So what you're doing here in statistical downscaling, you have a large-scale phenomena, and then how it is interacting with the local scale phenomena. For example, sometimes we say El Nino, that you must have heard of recently from last year. If it is El Nino, we get to have droughts, or if it is La Nino, we get to have floods. Some kind of correlation has happened between the that is a large scale phenomena that is happening in a larger area on the Pacific Ocean. So that is having a relationship between the local phenomena. For that matter, we can use any other meteorological variable having association or the correlation with the local scale phenomena, then use those statistical relationships to statistically downscale or to bring that information down to the region of interest. So this is that is the basis of statistically downscaling. You're establishing statistical relationship between two different variables, and then one is at local scale and one is at larger scale, and then you're using that relationship to bring estimate the information at the local scale. So this is the basic about statistical downscaling. And then we move before we do impact assessment, sometimes it's very important that you do downscaling, because when you're doing impact assessment, you're doing impact at a assessment at a regional scale, at a small watershed, or at a smaller spatial resolution at a small city or something. So you do the downscaling before coming to impact assessment. And in addition to statistical downscaling, I forgot to mention there is also called bias correction. So sometimes what happens is the climate model obviously it projects, or it actually simulates the historical climate, and also it projects the future climate. But then when you're comparing the historically observed climate with the historical climate simulated by the global climate model, there is a huge difference between there is a chance of having a bias by the model, because the model is based on lot of assumptions and lot of boundary conditions we have. So to reduce that amount of bias, we do bias correction techniques. It's again based on different methodologies that are available to do the bias correction. So after you do the bias correction, then you also statistically downscale it to a final resolution, and then you go for the impact assessment. Impact assessment is a process to evaluate the potential effects of climate change on variability on natural and human systems. So how it is affecting, for example, the stream flow. Impact is how the changing climate is impacting the availability of water, or how it is impacting the flood scenario in my city or in my watershed. So that kind of study is done, and it combines scientific research modeling and stakeholder input. So stakeholder is the end user of the output from a research study. So what exactly he wants to know? He wants to know what will be the available water in my region of interest, or he wants to know what will happen if I construct a dam. Will that be able to sustain to the amount of water that will come as an inflow? So that kind of information will be the requirement of a stakeholder. So it combines, and then the scientific research modeling. So it has to come to an understanding between the stakeholder and the scientific research community. And then it analyzes effects on various sectors, agriculture, water resources, health, infrastructure, ecosystem, using downscaled projections. So different sectors that I'll be discussing in the next slide. So why do we have to do the impact assessment? Why is it needed? So first thing is to identify vulnerabilities and risks. What are the vulnerabilities existing in the society or community because of the changing climate, and identify or estimate the risk. Inform adaptation and mitigation strategies based on the analysis done, and we can propose adaptation and mitigation strategies. And then it also helps in supporting decision making for sustainable development. So what are the three main changes that we are concerned about is the changes in precipitation, changes in temperature, and how the extreme weather is changing. And changes in any of these variables will impact different sectors. Some important sectors that I have listed out here are agriculture, ecosystems, water resources, infrastructure, and health related sectors, right? So how these sectors are being impacted? Mostly the agriculture is impacted by the changes in precipitation and also in temperature particularly. But the changes in precipitation particularly impacts the agriculture and water resources. So agriculture productivity depends on the water availability, and water resources again the water availability is impacted by the precipitation changes, and then indirectly affects the agriculture. And then change in temperature has an impact on again agriculture, and it has an impact on ecosystems. How the biodiversity is is actually prospering, right? With increasing temperature, it might lead to increase in dry spells, which might affect the sustainability of some kind of organisms or some kind of species, right? And then also change in temperature will cause health related issues, as we are aware of. And then the extreme events, be it floods or droughts, it can have an influence on infrastructure. It also has an influence on health related issues, the spread of diseases, or on the water quality, right? There are different things. The extreme events lead to the impacts. Changes in extreme events will change the characteristics of floods or drought. Its frequency, occurrence, or its severity. It can cause an impact on flood and drought characteristics. Then we also have the impact on agriculture will impact the crop yield reduction. Will mean crop yield. It will reduce the crop yield from a farm. And then changes in water availability will impact the will increase water scarcity if it is decreasing. These are certain way of putting the changes, the sectors, and how they are impacting, some way of putting together. It is a very generic way of presenting it, but there are different ways of doing it. So if you want to calculate how the climate is impacting a particular sector or particular thing, you have to identify there are some kind of climatic indices. These are developed by expert team on climate change detection and indices. Again, it is a program under World Climate Research Program. I have updated a link here. You can click to this and understand what is a climate index. It is a tool to describe the state of climate system and our monitored climate. It is often represented with a time series where each point in time corresponds to one index value. A climate index can be constructed to describe almost any atmospheric event. So there are different indices. I'll not go in detail to it, but there are the climatic indices are based on different atmospheric variables or meteorological variables that we calculate. There are indices based on temperature, indices based on precipitation, indices based on both temperature and precipitation, and there are other indices. So for example, indices based on temperature, here there is one such index I have listed out. This is a TR. This is the number of tropical nights, annual count of days when daily minimum temperature is greater than 20 degrees centigrade. So when the daily minimum temperature is greater than 20 degrees centigrade, we count that as a tropical night. So the temperature is within that minimum temperature that in particular. And that is so number of such nights number of such instances or number of such days are counted, and that can be used as one statistic to do climate change impact assessment. So I'll show you one study that I have done in a later slides. And then other than that, this is the indices based on temperature. Then we have indices based on precipitation. There are different indices. One index I am listing out here is standardized precipitation index. If you, some of you are aware of, this is popularly used in drought studies. Standardized precipitation index, drought severity is defined by this. Derived based on non-exceedance probability of monthly precipitation. Precipitation time series is fit to a suitable probable distribution, for example log normal, and then quantiles are extracted from the fit and index is computed by standardizing it. This is a standardized precipitation index. Then we have an index based on both temperature and precipitation. This is called standardized precipitation evapotranspiration index. This is again a very popularly used index in the drought studies, derived based on non-exceedance probability of monthly precipitation and evapotranspiration. That is the difference. You identify the difference between precipitation and evapotranspiration, P minus PET, and then you fit it to a suitable probability distribution and then extract the quantiles, and the indices are computed by standardization. So this is very briefly or very quickly going through computing SPI and SPEI. This is altogether takes around half an hour to understand how these are computed. So I'm just quickly giving you an information. So trying to present one study that I have done based using these indices. This is a case study that I have done for the assessment of impact of climate change on crop productivity. This is in Banas River Basin in Rajasthan. Here in this study, I have used temperature-based indices for this feature for identifying the crop productivity. Here the indices that I've used is number of days. I've counted the number of days with maximum temperature greater than 28 degrees centigrade during January to March. So during this period, I counted all the days that has temperature maximum greater than 28 degrees. This is for one crop, and then for the second, for a different crop, again the index is different. Tmax is greater than or equal to 30 degrees centigrade during October to March. Here you see January to March, and this is October to December. They have used two different indices. And then here, because I've used that temperature, because the day temperature needed for milking of wheat crops during January to March is 28 degrees centigrade. Right? If it is less than 28 degrees centigrade, there is a chance that it will the proper growth of wheat will not happen. Day's temperature needed for number of day temperature needed for milking of wheat crop during January to March. As you can see, there is a I've done a trend. So as you in January there is an increase the number of days with temperature greater than 28 degrees is increasing. In February again it is increasing, the number of days is increasing. In March, usually in March the temperature is more than 28 degrees, so there is not much change in March. Overall for the whole season January to March it is increasing. So this is how with this I can say the number of days with the temperature greater than 28 degrees is increasing. So actually the temperature should be 28 degrees centigrade or less. I forgot to mention that. If it is greater than 28 degrees, then the milking of wheat crop will not happen, and there will be loss in productivity of wheat. Because the temperature is increasing, there is a high chance that the productivity will be reduced in the future. Similar to that, I've used a second index where the maximum temperature is greater than 30 degrees, that is the daytime temperature is greater than 30 degrees for sowing of wheat crop during October to December. So this is the temperature needed, and again this is showing an increasing temperature. If this is showing a number of days are increasing during October to December, then that might have an impact on the productivity of wheat. So this is for the same crop, for one for sowing the wheat crop and then one for milking of the wheat. So we have to shifting of crops can also be one adaptation strategy that should be adopted with the change in temperature. Right? addition to that, I've also done for used precipitation-based index assessment of impact on climate change and water availability for the same study region. Precipitation time series for fit to log normal distribution and SPA is computed at various time scales. I'll just show you this using the precipitation-based index. What is the water availability in the basin will be. Historically, it is showing red in color. This is as you can see, the scale is minus. Red color is from minus 0.6 to minus 0.8. So that means there is a scarcity in this region in the historical period. As you can see in the future, this is early century, mid-century, and late century. This is going to yellow. This is yellow is it is going into the positive values. That means the availability of water is going to increase in the future. This is not from one particular model, but I have used multiple models. This is a multi-model scenarios. This is a multi-model minimum, multi-model mean, and multi-model maximum. So what is all this? It has to be instead of using, because one model cannot be used for impact assessment studies. So you have to use at least 2 or 3 models. And out of set of 36 models, how to pick 2 or 3 models again is a big question. So there are different methodologies to identify the best suited models for the region of interest. So you can adopt any particular methodology and identify the models of interest, and then the presenting the results, you cannot use output from one single model, and you have to take a multi-model statistics of. So this is the multi-model result from multi-models. Right. This is for water availability in April using the precipitation based index. Then I've used index based on precipitation and temperature, that is SPA, which I have discussed earlier. This is again for the same study region, for the same time period, and then the projections, as you can see here. Historical period based on the precipitation and temperature data. The water availability in the historical period is relatively better based on this. Yellow represents, yellow means is a positive value and the red means a negative value. But then as you go into the future, it's going to worsen. It's going to the severe drought situation. Earlier we have used only precipitation as an indicator. That's why we are saying that there is there is not enough supply in the historical period, but there is going to be enough supply in the future. But then in the index based on both temperature and precipitation, we are having a different result. So this is all together how you use and what kind of index you use for the impact assessment studies. You have because there is a lot of indices available, and out of this, what you are choosing and how you are choosing, it becomes a big question, and depending on the objective of the study, you have to identify the indices that can be useful for the impact assessment study. So coming to hydrological impact assessment, so earlier what I have done, I've tried to see the impact of changes in temperature and precipitation on agricultural productivity. Similarly, you can also do it for the water availability. It examines how climate change and variability is affecting the water resources. Evaluates impacts on precipitation, runoff, river flows, groundwater, and water quality. Also, it can be modeled. It is critical for water management, disaster mitigation. It actually helps to understand or improve the adaptation strategies, develop adaptation strategies. Methodology.
Sorry to disturb you. Excuse me, sorry to disturb you, but just a gentle reminder that you have to conclude the session by summarizing key points.
Yeah. I'm just
then
finishing.
We have to take question answer also.
Yeah, sure. I'm just finishing with 2 more slides. So this is the methodology for hydrological impact assessment. You have to define the scope and study area, and then for impact assessment, you have to have a CMIP 6 scenarios. We also have observed data, as I mentioned, from different climate models or the observed from the meteorological station. Then you use some kind of hydrological model. Recently, I've done such study using a WIC model, variable infiltration capacity model. Other than that, you also have a SWOT model. You have MIC models. You can use any hydrological model to depending on the variable you want to simulate, choose a model, and then simulate impacts and evaluate risks to water availability and quality. Based on the simulations, you can generate with different scenarios, and then based on the scenarios generated, you can recommend adaptation strategies. These are some of the challenges in hydrological impact assessment. There are data limitations, as I mentioned. This is a very basic disadvantage. Uncertainty in climate projection. There are different assumptions made in the climate model, so that leads to a lot of uncertainty. For that matter, there are uncertainties associated with the hydrological models, uncertainties associated with the climate projections, climate models, and then uncertainty associated with the downscaling approach, uncertainty associated with the bias correction approach. There are different, it becomes very complex. And then it's a complex interactions cannot be incorporated into the climate and hydrological model. So complex, some important feedbacks might be missed, and then there is a scale issue. Again, local dynamics are not captured. So these are the limitations. And I think I have covered almost everything, where you get the data from, what are the data sets available, what is a climate model, what is IPCC, CMIP6, SSPs, downscaling, and impact assessment, how you can do. I hope this gives you an overview to conduct research based on your research question. If there are any questions, I'll be happy to answer, and this is my contact. You can contact us anytime. Thank you.
Thank you, sir. Thank you so much. Audience, any
Thank
questions you
you,
want to ask?
Thank you, sir. Very informative session. You have covered from very basic till the detailed hydrological impact analysis. Very informative, sir.
Thank you very much, ma'am. Thank you. I hope this helps the faculty.
There is Prashant Vashisht who wants to ask question. Unmute yourself and ask the question.
I think it may be done by mistakenly.
Okay, fine.
Any other participant want to ask the question?
There is.
Hello, am I audible?
Yes,
Yeah.
yes, you're audible.
Am I audible, ma'am?
Yes,
Yes.
Good evening. This is Nitin Savalkar from BVCOEW Pune. I'm actually doing my research work in this area only, but my area is in ocean engineering. One question is there in my mind. Sir, how to correct or how to do the bias corrections for a data? Suppose I am having the reanalysis data set or the reanalysis data set or the output from any of the numerical modeling. And if I'm going to have its comparison with respect to historical observed data, and if I'm not getting the correct values or the correlation coefficient or error measurements are quite high, at that time you said that biases might be get introduced. So how to correct these biases, sir?
So there are different methods that are available to do the bias correction. Basically, when we do bias correction, we go for statistically bias correction, right? Dynamic downscaling, if you are a hydrologist, I think it's basically impossible to do a dynamic downscaling. So we go for statistically downscaling. When you're doing statistically downscaling, there are different approaches like delta change method, quantile mapping approach. So you try to remove when you're using a delta change method, you try to remove the how much amount of bias is there. You try to remove it from the modeled data set. So whatever you identify the difference between the observed, right, the reanalysis data set and the model data set, you try to remove that.
Okay. Is it necessary that we have to do the bias correction? If it is not done, is it fine? Or
No,
you will not
depending on what projected data set you're using, what kind of data set you're using for climate change impact assessment. Is it from NASA, or are you using the raw data set from the WCRP?
I'm using it from CMIP6 GCM data.
No, I understand CMIP6 data set, but what is the source? Because NASA has already provided bias corrected data, right? If you are
Okay.
using the already bias corrected data, then it's not necessary that you need further bias correction.
The data set is not bias corrected, sir. We need to, that means it is in raw form.
Yeah, if it is a raw data set, if the bias is too high, then you definitely have to do bias correction.
Okay. And sorry to extend my question again. You mentioned something about multi-model ensemble.
Yes, multimodal
Yeah, yeah,
ensemble.
yeah, yeah. Sir, what are the various ways with which we can have the ensemble of GCM data?
When you, I didn't understand, like various methods means you either provide multimodal mean, you provide the multimodal maximum. So it all depends on the number of models or how you are actually selecting the models.
Because I'm having the input in the form of velocity. And
Mean
I just
velocity.
need to do the ensemble of this data. So how should I do the ensemble? Because ensemble is nothing but the average out of that particular data. If I'm doing the average of that velocity, suppose it is -3 is one of the component and -2 is one of the component. The average of these two is -3 or -3 -2. Yeah. So if I'm having that kind of data set, how we can do the ensemble?
Okay. The negative data, actually I haven't came across that, but I think that can be done. Even if it is -3, -2, that can also be taken average.
No, if it is taken average -2, -3 and -2, that will become -5 divided by 2. That will become -2.5. If it is fine. Suppose I am having, suppose it is -3 and +2. That will become 0,
That will
but we
become
don't
0.
have the velocity as 0, right?
Yeah.
Yeah. So do we have any lead so that we can clarify this doubt?
Actually, tomorrow I think there is one lecture by Dr. Vishal Singh. I think tomorrow, day after tomorrow.
Okay.
You can ask him. But actually the problem is we haven't done with the velocity data set, right? So we usually have temperature minimum and maximum. So that
Yeah.
way,
It is quite easy to have the average out because we don't have the negative and positive values of the temperature.
You don't
But
really have to go for averaging. You can go for multimedia minimum, multimedia maximum, or you can go somewhere in between multimedia, I'm sorry, multimodal minimum and
yeah.
multimodal maximum. So
Okay.
depending on the number of models or the type of models you're selecting, you can select any statistic. You don't have to go for average. If the average is actually hindering your result, I think that is better not to go with average.
Yeah. Okay. Thanks a lot, sir. Thank you so much. Your session was very much informative and we really enjoyed it, sir. It was very much informative.
Thank you very much. Thank you.
Yeah, thank you, organizers as well, because the sessions are quite useful. Thank you so much for organizers.
Yeah, thank you,
Thank you,
Nitin
sir.
sir.
Thank you.
Any other questions from participants?
Yes, good evening. I am Dr. Vinesh Nair.
Hi.
Am I audible?
Yes. Please go ahead.
Yeah. It was a nice presentation.
Thank you.
And regarding the impact assessment, we need to use different climate indices, right?
Yeah.
So all these indices are standardized or depending upon the.
Yeah, the
It is
indices are standardized. As I've given the link in the presentation, ETCCDI. I
Okay.
think that is called ETCCDI. Just one second. I think that is a program under WCRP. They have standardized some indices.
Okay. Or depending
Expert
upon the
team on
nature of
climate
work.
change detection. Depending on the nature of work, you have to choose because ETCCDI has a set of indices that are used for climate change impact assessment. So depending on the nature of work or the objective of your study, then you can select a appropriate index.
appropriate indices. Okay, okay. Thank you, thank you.
Any other question? Okay, I think now no question.
Yeah.
So we are moving towards the end of this end of the day. Both the sessions are very good. Now, on behalf of Bharati Vidyapeeth College of Engineering for Women, Pune, I extend my heartfelt gratitude to our esteemed speaker, Dr. Sunil, for delivering such a thought-provoking and enriching session. Your expertise and insights have been truly valuable to all of us. So I also thank all the participants for their active engagement and enthusiasm throughout the session. So kindly join tomorrow's session on time. Link will be provided
Kanchan,
on the WhatsApp group.
Kanchan, sorry to interrupt you. I think one more
Yes.
question is there.
Okay. Seema madam, you want to ask something?
I think by mistake it's been up.
Yes.
Seema madam. Seema madam, you want to ask question?
I think Kanchan by mistake she has done. I think.
Yes.
Yes.
So I have shared feedback link of both the sessions on chat as well as on WhatsApp group. So please fill the feedback today only, and tomorrow join the session. Link will be again provided in WhatsApp group. So thank you once again and good night.
Thank you very much and good night. Thank you for
Thank
the
you very much.
opportunity.
Thank
Thank you, Sunil sir. Thank you.
Thank you.
Thank you, Sunil sir.
Thank you.
It's
Thank you.
great
Bye.
session.
Thank you very much. Thank you.
Thank you.